Hi everybody, I'm Lawrence Moroney from the TensorFlow team at Google. We know you have lots of questions about TensorFlow, so we have this new YouTube show called Ask TensorFlow, where we'll try to answer your questions.
What is the difference between TensorFlow Mobile and TensorFlow Lite?
One's mobile, the other's light.
That's right. But going forward, TensorFlow Lite should really be seen as the evolution of TensorFlow Mobile.
Simply post your questions on social media with the hashtag AskTensorFlow, and we'll answer a bunch of them in every episode. So be sure to subscribe.
Welcome to Ask TensorFlow, where we'll be answering all of your questions about TensorFlow Lite and Swift for TensorFlow. I'm Paige Bailey.
And I'm Daniel Sitanaika, and I work in DevRel for TensorFlow Lite.
Excellent. So with that, let's get started with our first question. This is from Zongjun Zhang and was submitted via YouTube. Is RNN, LSTM, quantization-aware training, and Toco conversion in TF Lite available in TensorFlow 2.0? That's a lot of acronyms in a sentence, and it sounds like a question that's for you, Dan.
It is indeed. So I can say, first of all, yes, all of these things are either available or coming in TensorFlow 2.0. With regards to RNNs and LSTMs, we actually just published a guide on how you can use these with TensorFlow Lite. You can find that on our docs. With Toco conversion, the converter works great with 2.0, and we also have a guide on how to do that. And with quantization-aware training, right now we're recommending you check out post-training quantization. We've actually just published some new documentation on that, and it works really, really well. But if you want to use quantization-aware training, we're going to have support for that for TF 2.0 coming very soon.
Excellent. And all of those links that Dan mentioned are going to be listed in the comments section of this YouTube video, so make sure to check them out. For the next question, is there any tutorial or example for text processing models in TensorFlow Lite, aside from the pre-trained Smart Reply example? This is from Shubham.
All right, so right now, Smart Reply is our main example that involves text processing. However, we are working on a lot of new models right now. And so if you sign up for the TF Lite mailing list, you'll be able to get notified when we release a bunch of new models that you can play with.
Excellent. And a link to that TF Lite mailing list will also be placed in the comments section of the video.
All right, so our next question is from Sohaib Arif, who asks, is Swift for TensorFlow for iOS programming?
That's an excellent question, Sohaib. So Swift is absolutely for iOS programming. You've probably used it if you were building iOS apps. Swift for TensorFlow will be able to deploy to iOS devices. However, right now we only have support for macOS and also for Linux. But if you're interested in this space, absolutely stay tuned by joining the Swift at tensorflow.org mailing list, as well as our weekly open design meetings that happen every Friday at 9 a.m. Pacific time. So thanks so much for the question. For our next question, it also sounds like a TF Lite question from Karayun, is will there be a commodity device that I can use for TPU inferencing?
Awesome. So the answer is yes. And you may have heard of something called the Edge TPU. It's basically like a tiny low power version of our TPU machine learning accelerators that you can embed in hardware that you're producing. So imagine you're making a consumer product or an IoT device. You can take the TPU, add it to that device, and get accelerated inference at the edge. So we've created something called the Coral platform, which gives you the end-to-end developer tooling to be able to do this. So you can start off with dev boards that you can order online. And once you've prototyped your application, you can have all the tools to go into production and incorporate the hardware into your own products. So that's called the Coral platform, and you can find it at coral.withgoogle.com. It's super exciting.
Excellent. And that's so cool that you can have TPUs outside of a data center that you just order online and have it delivered directly to your house.
Absolutely. And small enough that it works in your pocket.
That's amazing. Another TF Lite question. So does TF Lite only work on these Coral dev boards? This is from Christian Rivera.
All right, so actually TF Lite is the way that you work with ML and TensorFlow on Coral dev boards, but TF Lite works across the board. We cover basically every platform you can think of. So from like mobile phones, Android and iOS, through to IoT platforms and embedded Linux, like things like the Raspberry Pi, all the way down to tiny microcontrollers with our new TensorFlow Lite for microcontrollers product. And you can actually run TensorFlow Lite on the server as well. It's basically just a streamlined, stripped down, super fast, optimized version of TensorFlow for deploying machine learning on device.
Excellent. And what I love too is that it supports so many different languages, right? So if you're not a Python person, you can use Swift or you can use Java or a whole host of others.
Absolutely, yeah. Even if you're writing C++ on tiny embedded devices, you can use our libraries. So it's pretty
Excellent.
cool.
Our next question is also about Edge TPUs, so I guess these must be pretty popular. Will Edge TPUs be available to purchase in other countries? This is from Yao Ouyang asked on YouTube.
All right, excellent question. So, absolutely, Edge TPUs are available all over the world, currently available in over 30 countries. And the place to go and find them is coral.withgoogle.com.
Excellent. And Coral just recently released their compiler as well. Didn't they open source it?
Yeah, so Coral's compiler is now open source, so you can convert your models with TensorFlow Lite, run them through the Coral compiler, and then deploy them to Edge TPU.
Excellent.
All right, so next question from Raveen Gouda is what about Android things? Does TensorFlow 2.0 support them?
Absolutely. And that's kind of a double whammy, right? So, Swift for TensorFlow is certainly supported on Android devices. You're capable of running Swift on Android, and it pairs quite nicely with Kotlin. They're pretty syntactically identical. But TensorFlow Lite has a whole host of options on Android, right, Dan?
Yeah, absolutely. So TensorFlow Lite was really built from the ground up to work with these types of mobile and embedded operating systems. So whether you're using Android or iOS, we have a ton of support and documentation and libraries. So if you want to access hardware acceleration, for example, on Android, you can use our GPU delegate if your device supports it. We have libraries in Java and Kotlin. So basically, yeah, you're good to go. All right, so our next question from Sahai Barif is what platforms are supported by Swift for TensorFlow?
Right now, and this is an excellent question, Sahib, is right now we support Linux as well as Mac OS. But we have plans to support iOS and also Android, and you can certainly run Swift on both iOS and Android devices. One of the cool things about Swift for TensorFlow is that it's an infinitely hackable machine learning framework, and Swift is an infinitely hackable language that's essentially just syntactic sugar for something called the LLVM. So we anticipate that support for mobile devices will land before the end of the year, but if you want to stay up to date, again, join the Swift at TensorFlow.org mailing list. Our next question is also about TensorFlow Lite. Will there be support in the Python API for exporting object detection models? So for example, after transfer learning to TF Lite.
Awesome. So that's a great question because it lets me talk about the TensorFlow Lite converter. And so it doesn't really matter what type of model you want to use with TensorFlow Lite. Basically, the workflow is that you'll train your model with TensorFlow, export it to a format like saved model, and then you can load it into the TensorFlow Lite converter, which will handle basically taking that model, creating it in a file format which is optimized for use on mobile, so it's very small and efficient, and also doing a bunch of other optimizations. Some of them are optional that can increase performance of your model when it's running on device. So pretty much whatever kind of model you're using, you can use the converter. And for a bunch of models, for example, for object detection, you can actually go to tensorflow.org/lite/models, and we have them available for download. So you don't even necessarily need to do the conversion yourself.
That's amazing. And I also love that saved model is so well represented across the entire TensorFlow ecosystem. So if you do create that model using the Python API, and you convert it to saved model, you would be able to deploy it to browsers with TensorFlow.js, to all of these great mobile use cases, to embedded devices, and anywhere you would want to place machine learning.
Yeah, it's really exciting that we've got this format that's just at the heart of everything and lets you use your model everywhere.
Yep, machine learning with no boundaries.
Awesome. So our next question is, why is it currently so difficult to integrate and use custom C++ or CUDA operations in TensorFlow, and especially TensorFlow serving? And are there any plans to make this process easier for production?
Excellent. So I love this question, and I'm really excited to be able to say that yes, Swift for TensorFlow has plans to give you the ability to import C headers, C++ headers, and to also give really performant C++ interop. We also envision a world with MLIR where you would be able to write custom CUDA kernels from within a Jupyter notebook. So certainly recommend taking a look at the C++ interop capabilities and C header imports available to you in Swift for TensorFlow. Swift for TensorFlow also targets the TensorFlow graph representation, which means it's extensible across the entire ecosystem. And also take a look at that MLIR documentation.
All right, so the next question from Katayun is, I had some problems when using Keras and TensorFlow with OpenCV.
Yeah.
Are there any improvements in TensorFlow 2.0?
So that's a great question. There are improvements for doing image processing operations with TensorFlow 2.0, both as part of TF-Image and as part of TensorFlow add-ons, which is a community-supported package for a number of Keras layers and losses and great image preprocessing steps. We also have an RFC out for preprocessing layers. But if you really want to use OpenCV in a performant way by directly importing the C library, you would be able to use it with Swift for TensorFlow. So there's a great example from Jeremy Howard, the creator of FastAI, on how he was able to build a custom data import pipeline using C headers and OpenCV that was twice as fast as TF data. So if you're a fan of OpenCV, if you want to use OpenCV, the way that you use it currently, which is probably with C or C++, Swift for TensorFlow might be an excellent option. And if not, we do have a number of support features available in TensorFlow 2.0.
Very cool.
Our next question, does TensorFlow have any API that can do AutoML, such as Azure ML SDK? And this is from Mobub. That sounds like a you question.
Yeah, so I would say the best thing to do if you're interested in AutoML is look up this product called Cloud AutoML from Google, and basically allows you to do a bunch of ML stuff in a semi-automated way in the cloud. So you can train models to do cool stuff using our tooling and then export the model to use wherever you need to use it.
Absolutely. And it searches across, in an intelligent way, so not a brute force search, the entire problem space for machine model optimization. We also have something called Keras Tuner. So if you want to have a little bit more control over the hyperparameter tuning, you can do that on your own as well. But I think you're right that Cloud AutoML is probably your best bet.
Good place to start.
Yeah.
All right, so our next question is, what about Kotlin for TensorFlow?
So that's another double whammy, right? So we don't have Kotlin bindings for TensorFlow, but I do think that you have Kotlin support for TF Lite. Is that correct?
Yeah, so you can use our TF Lite library from within Kotlin, super easy.
Excellent. So I guess we do, but not from the perspective of Swift for TensorFlow or the Java bindings for the language directly. So our next question is, can a deep learning model be miniaturized automatically? And that sounds like a TF Lite scenario.
Yeah, and this is a great question to answer because we've just published something called the Model Optimization Toolkit, which basically documents how to do exactly this. So we have a set of tools that can do everything from taking a saved model and re-encoding it into a different, more space-efficient file format called a flat buffer for deploying on mobile devices. And that's something you'd use the TensorFlow Lite converter to do, all the way through to quantization, where you're actually reducing the precision of the numbers in the model so that the model takes up less space on disk and takes less time to execute, but potentially doesn't really lose any accuracy. So it's always kind of magical. So those are some of the techniques we have available right now, but in the future, we're going to be adding more. So you should sign up to the TensorFlow Lite mailing list to get updates on this and check out the Model Optimization Toolkit.
Absolutely. And if you've used it, I think we would love to hear feedback about it. So make sure to share your experience on the TF Lite mailing list.
Absolutely. All right, so the next question is, regarding tf.data, do you guys have any new APIs to directly load audio files like waves, etc., instead of going through the extra conversion steps to convert to TF records?
Excellent. That is a great question. And I completely understand the struggle of having to migrate between WAV file formats to TF records and dealing with TF data pipelines. We're adding support in TensorFlow 2.0 through something called tf.io. So if you have specialized data input formats or export formats, that could be a great option. But I also suggest very strongly that you take a look at Swift for TensorFlow. That way you can import WAV files exactly as you would in C or C++. And I can also place a link in the video description below showing precisely how to import those audio files. So thanks so much for the question. I'm really excited to see what you create.
All right, so our next question from Jordan is, do you have any plans to add support for constraints or even better, auto diff on manifolds? It would be so nice to do optimization where some parameters live in SO3, for example.
Excellent question again. So AutoDiff is very near and dear to my heart, and it's something that we're working very closely on with Swift for TensorFlow. One of the magical things about Swift is that any function, so anything that you can imagine, adds or multiplies or custom functions, they're all differentiable. So I strongly suggest that you take a look at our design document for AutoDiff. It's just recently been released, and we'll place a link in the video description below. And let us know what you build, Jordan. Really excited to see it.
All right, thank you so much for all your awesome questions. And just as a reminder, if you have a question that you'd like us to answer on Ask TensorFlow, post it on social media with the hashtag AskTensorFlow.
And make sure to check out all of those great links that we have in the video description below. We're really excited to see what you think, and we can't wait to hear the new questions that you ask. So thanks so much for joining us today. I'm Paige Bailey.
And I'm Daniel Sitanaika.
And this has been Ask TensorFlow.
Hi, I'm Robert Crow, and today I'm going to be talking about TensorFlow Extended, also known as TFX, and how it helps you put your amazing machine learning models into production. This is the first episode in our 5-part series on real-world machine learning, which will help you get up to speed on using TFX to create your own production machine learning pipelines. In today's episode, we'll be asking the question, what exactly is this TFX thing anyway? Let's find out. When we think about ML, we usually only think about the great models that we can now create. After all, that's what all the research papers are focused on. But when we want to take that amazing model and make it available to the world, we need to think about all the things that a production solution requires. So, that's why we have TFX, to build production pipelines so that we can offer our amazing models to the world. Google created TFX because we needed it, and there was nothing already available that could meet our needs. Google does a ton of ML, and not just Google, but all of the alphabet companies. There's ML in almost everything we do. In fact, TFX wasn't the first ML pipeline framework that Google created. It evolved out of earlier attempts and is now the default framework for the majority of Google's ML production solutions. And now, Google is open sourcing TFX and making it available to everyone. And it's not just Google. TFX has had deep impact on our partners, including Twitter, Airbnb, and PayPal. As ML developers putting a model into production, what do we need to think about? First, when we start planning for developing an ML application, we have all the normal ML things to think about. That includes getting labeled data if we're doing supervised learning, and making sure that our data set covers well the space of possible inputs. We also want to minimize the dimensionality of our feature set while maximizing the predictive information it contains. And we need to think about fairness and make sure that our application won't be unfairly biased. We also need to consider rare conditions, especially in applications like healthcare, where we might be making predictions for conditions that only occur in rare but important situations. And finally, we need to consider that this will be a living solution that will evolve over time as new data flows in and as conditions change, and plan for life cycle management of our data. But in addition to all that, we need to remember that we're putting a software application into production. That means that we still have all the requirements that any production software application has, including scalability, consistency, modularity, and testability, as well as safety and security. We're way beyond just training a model now. By themselves, these are challenges for any production software deployment, and we can't forget about them just because we're doing ML. How are we going to meet all these needs and get our amazing new model into production? We don't pretend to have all the answers. This is an evolving field within the ML community, and we welcome contributions. If you're interested in a more in-depth discussion of the challenges of machine learning in production environments, this is a great paper. That's what TFX is all about. TFX allows you to create production ML pipelines that include many of the requirements for production software deployments and best practices. It starts with ingesting your data and flows through data validation, feature engineering, training, evaluating, and serving. In addition to TensorFlow itself, we've created libraries for each of the major phases of an ML pipeline: TensorFlow data validation, TensorFlow transform, and TensorFlow model analysis. TFX implements a series of pipeline components which leverage these libraries, which in this diagram are in orange, and allows you to create your own components too. To tie all this together, we've created some horizontal layers for things like pipeline storage, configuration, and orchestration. These layers are really important for managing and optimizing your pipelines and the applications that you run on them. We'll be discussing those more in later episodes. For now, that should give you an idea of what we're talking about when we think about implementing a production ML pipeline with TFX. In our next episode, we'll discuss how TFX pipelines actually work. For more information on TFX, visit us at tensorflow.org/TFX, and don't forget to comment and like us below, and thanks for watching. Hi, I'm Robert Crow, and today I'm going to be talking about TensorFlow Extended, also known as TFX, and how it helps you put your amazing machine learning models into production. This is episode 2 of our 5-part series on real-world machine learning in production. We covered a lot in episode 1, so if you haven't seen that yet, I'd really recommend watching it. In today's episode, we'll be asking the question, how do these pipeline things work? Let's find out. TFX pipelines are created as a sequence of components, each of which performs a different task. Components are organized into directed acyclic graphs, or DAGs, but what exactly is a component? A TFX component has 3 main parts: a driver, an executor, and a publisher. 2 of these parts, the driver and publisher, are mostly boilerplate code that you could change, but probably will never need to. Where you insert your code and do your customization is really in the executor. The driver handles coordinating job execution and feeding data to the executor. The publisher takes the results of your executor and updates the metadata store, which we'll talk about more in the next episode. But the executor is really where the work is done for each of the components. So first, we need a configuration for our component, and with TFX, that configuration is done using Python. Next, we need some input for our component and a place to send our results. That's where the metadata store comes in. We'll talk more about the metadata store in our next episode, but for now, just be aware that for most components, the input will come from the metadata store, and the result will be written back to the metadata store. So, as our data moves through the pipeline, components will read metadata that was produced by an earlier component and write metadata that will probably be used by a component farther down the pipeline. There are some exceptions, like at the beginning and end of the pipeline, but for the most part, that's how data flows through a TFX pipeline. To organize all these components and manage these pipelines, we need orchestration. But what is orchestration exactly, and how does it help us? If all that you need to do is kick off the next stage of the pipeline, task-aware architectures are enough. You can simply start the next component as soon as the previous component finishes. But a task and data-aware architecture is much more powerful, and really almost a requirement for any production system because it stores all the artifacts of every component over many executions. Having that metadata creates a much more powerful pipeline and enables a lot of things which would otherwise be very difficult. So TFX implements a task and data-aware pipeline architecture. We'll be discussing that in detail in the next episode, so stay tuned. To put an ML pipeline together, define the sequence of components that make up the pipeline, and manage their execution, we need an orchestrator. An orchestrator provides a management interface that we can use to trigger tasks and monitor our components. One of the ways that TFX is open and extendable is with orchestration. We provide support for Apache Airflow and Kubeflow out of the box, but you can write code to use a different orchestrator if you need to. So if you've already got an orchestrator that you like, you can use it with TFX. We don't force you to change. Here's what a TFX DAG, or Directed Acyclic Graph, looks like in two different orchestrators, Airflow and Kubeflow. It's the same DAG, just two slightly different ways of displaying it. In our next episode, we'll discuss the role of metadata and how it helps us create much more powerful pipelines. For more information on TFX, visit us at tensorflow.org/TFX, and don't forget to comment and like us below, and thanks for watching. Hi, I'm Robert Crow, and today I'm going to be talking about TensorFlow Extended, also known as TFX, and how it helps you put your amazing machine learning models into production. This is episode 3 of our 5-part series on real-world machine learning in production. We've covered a lot so far in episodes 1 and 2, so if you haven't seen those yet, I'd really recommend watching them. In today's episode, we'll be asking the question, why do I need metadata? Let's find out. TFX implements a metadata store using ML Metadata, which is an open source framework for doing exactly that, storing ML metadata. It's stored in a relational database, so basically any SQL-compatible database will do. But what exactly do we store in our metadata store? First, we store things like the models that we've trained, the data that we trained them on, and their evaluation results. We refer to the things that we store in metadata as artifacts, and artifacts have properties. The data itself is stored outside the database, but the properties and location of the data object is kept in the metadata store. Next, we keep execution records for every component, each time it was run. Remember that an ML pipeline is often run frequently over a long lifetime, as new data comes in or as conditions change, so keeping that history becomes important. Finally, we also include the lineage or provenance of the data objects as they flow through the pipeline. That allows us to track forward and backward through the pipeline to understand the origins and results of running our components as our data and code changes. This is really important when we need to optimize or debug our pipeline, which would be very hard without it. Now that we have some idea what's in our metadata store, let's look at some of the functionality that we get from it. First, having the lineage or provenance of all of our data artifacts allows us to trace forward and backward in our pipeline. For example, to see what data our model was trained with or what impact some new feature engineering had on our evaluation metrics. In some use cases, this ability to trace the origins and results of our data may even be a regulatory or legal requirement. Remember that it's not just for today's model or today's results. We're also interested in understanding how our data and results change over time as we take in new data and retrain our model. We often want to compare to model runs that we ran yesterday or last week to understand why our results got better or worse. Production solutions aren't one-time things. They live for as long as you need them, and that can be months or years. We can also make our pipeline much more efficient by only rerunning components when necessary and using a warm start to continue training. Remember that we're often dealing with large data sets that can take hours or days to run. If we've already trained our model for a day and we want to train it some more, let's start from where we left off instead of starting over from the beginning. That's only possible if we've saved our model in metadata. We can also make our pipeline much more efficient by only rerunning our other components when the input or code has changed. Instead of rerunning the component again, we can just pull the previous result from cache. For example, if a new run of the pipeline only changes parameters of the trainer, then the pipeline can reuse any data preprocessing artifacts such as vocabularies, and this can save a lot of time given that large data volumes make data preprocessing expensive. With TFX and ML metadata, this reuse comes out of the box, while the user sees a simpler run pipeline interface and does not have to worry about manually selecting which components to run. Again, that can save us hours of processing. That's much easier if we've saved our components' input and results in metadata. In our next episode, we'll discuss orchestration and dive into each of the components that come standard with TFX. For more information on TFX, visit us at tensorflow.org/TFX, and don't forget to comment and like us below, and thanks for watching. Hi, I'm Robert Crow, and today I'm going to be talking about TensorFlow Extended, also known as TFX, and how it helps you put your amazing machine learning models into production. This is episode 4 of our 5-part series on real-world machine learning in production. We've covered a lot so far in episodes 1 through 3, so if you haven't seen those yet, I'd really recommend watching them. In today's episode, we'll be talking about distributed processing and components. Let's get started. Let's talk about the components that come standard with TFX. But before we talk about the standard components, let's talk about Apache Beam. To handle distributed processing of large amounts of data, especially compute-intensive data like ML workloads, you really need a distributed processing pipeline framework like Apache Spark or Apache Flink or Google Cloud Dataflow. So several of the TFX components run on top of Apache Beam, which is a unified programming model that can run on nearly any execution engine. Beam allows you to use the distributed processing framework you already have, or choose one that you'd like, rather than forcing you to use the one that we chose. Currently, Beam Python can run on Flink, Spark, and Dataflow runners, but new runners are being added. It also includes a local runner, which enables you to run a TFX pipeline in development on your local system, like your laptop. So in the case of the transform component, for example, we use Beam to perform feature engineering transformations, like creating a vocabulary or doing PCA. That could be running on your Flink or Spark cluster, or on the Google Cloud using Dataflow, or, because it uses Beam, you could migrate between them without changing your code. In the case of the trainer component, we're really just using TensorFlow. Remember when all we were thinking about was training our amazing model? That's the code we're using here. Note that currently, TFX only supports 1.x models and TF estimators. In the case of some components, we're really only writing Python. The pusher component, for example, only needs Python to do its job. So, when we put all these together and manage it all with an orchestrator, this is what it looks like. On the left, we're ingesting our data, and on the right, we're pushing our saved models to one or more of our deployment targets. That includes modeled repositories like TensorFlow Hub, or JavaScript environments using TensorFlow JS, or native mobile applications using TensorFlow Lite, or server farms using TensorFlow Serving, or all of the above. So now let's look at each of these components in a little more detail. First, we ingest our input data using ExampleGen. ExampleGen is one of the components that runs on Beam. It reads in data, splits it into training and eval, and formats it as TF examples. This is what the configuration looks like for ExampleGen. Very simple, just 2 lines of Python. Next, we have StatisticsGen. StatisticsGen makes a full pass over the data using Beam, 1 full epoch, and calculates descriptive statistics for each of our features. To do that, it leverages the TensorFlow Data Validation Library, which includes support for some visualization tools that you can run in a Jupyter notebook. That lets you explore and understand your data and find any issues that you may have. This is typical data wrangling stuff, the same thing we all do when we're preparing our data to train our model. Here's a better look at the visualization tools. Right away, we can see that we might have a problem with our trip start hour feature at 6 a.m., where we don't have a lot of data to make predictions. Our model's performance at that time of day might not be so great unless we go get some new data. Our next component, SchemaGen, also uses the TensorFlow Data Validation Library. It looks at the statistics which were generated by StatisticsGen and tries to infer the types for each of our features, including the range of categories for categorical features. We can adjust the schema as needed, like adding new categories that we expect to see. Our next component, Example Validator, takes the statistics from StatisticsGen and the schema, which may be the output of SchemaGen or the results of user curation, and looks for problems. It looks for anomalies, missing values, or values that don't match our schema, and produces a report of what it finds. Remember that we're taking in new data all the time, so we need to be aware of problems when they pop up. Transform is one of the more complex components and requires a bit more configuration as well as additional code. Transform uses Beam to do feature engineering, applying transformations to your features to improve the performance of your model. For example, Transform can create vocabularies or bucketize values, or run PCA over your input. The code that you write depends on what feature engineering you need to do for your model and data set. Transform will make a full pass over your data, 1 full epoch, and create 2 different kinds of results. For things like calculating the median or standard deviation of a feature, numbers which are the same for all examples, Transform will output a constant. For things like normalizing a value, values which will be different for different examples, Transform will output TensorFlow ops. Transform will then output a TensorFlow graph with those constants and ops. That graph is hermetic, so it contains all of the information you need to apply those transformations, and will form the input stage for your model. That means that the same transformations are applied consistently between training and serving, which eliminates training-serving skew. If instead you're moving your model from a training environment into a serving environment or application, and trying to apply the same feature engineering in both places, you hope that the transformations are the same, but sometimes you find that they're not. We call that training-serving skew, and Transform eliminates it by using exactly the same code anywhere you run your model. Now we're finally ready to train our model, the part of the process that you often think about when you think about machine learning. Trainer takes in the Transform graph and data from Transform and the schema from SchemaGen, and trains a model using your modeling code. This is normal model training, but when training is complete, Trainer will save two different saved models. One is a normal saved model that will be deployed to production, and the other is an eval saved model that will be used for analyzing the performance of your model. The configuration for Trainer is what you'd expect. Things like the number of steps and whether or not to use warm starting. The code that you create for Trainer is your modeling code, so it can be as simple or complex as you need it to be. To monitor and analyze the training process, you can use TensorBoard, just like you would normally. In this case, you can look at the current model training run or compare the results from multiple model training runs. This is only possible because of the ML metadata store, which we talked about in our last episode. TFX makes it fairly easy to do this kind of comparison, which is often revealing. Now that we've trained our model, how do the results look? The evaluator component will take the eval saved model that Trainer created and the original input data and do deep analysis using Beam and the TensorFlow model analysis library. It's not just looking at the top-level results across the whole data set. It's looking deeper than that, at individual slices of our data set. That's important because the experience that each user of our model has will depend on their individual data point. Our model may do well over our entire data set, but if it does poorly on the data point that a user gives it, that user's experience is poor. We'll talk about this more in our next episode. So now that we've looked at our model's performance, should we push it to production? Is it better or worse than what we already have in production? We don't want to push a worse model just because it's new. So the model validator component uses Beam to do that comparison, using criteria that we define to decide whether or not to push the new model to production. If Model Validator decides that our new model is ready for production, then Pusher does the work of actually pushing it to our deployment targets. Those targets could be TensorFlow Lite if we're doing a mobile application, or TensorFlow JS if we're deploying to a JavaScript environment, or TensorFlow Serving if we're deploying to a server farm, or all of the above. So now hopefully we've given you a basic understanding of TFX and ML pipelines in general, and some of the issues around putting an ML application into production. And remember, TFX is open source. We want you to help contribute to making TFX better. In our next episode, we'll look at a real-world example of why analyzing model performance is important to your business. For more information on TFX, visit us at tensorflow.org/TFX. And don't forget to comment and like us below, and thanks for watching.
Airbnb is an online marketplace. We have over 5 million different homes in 81,000 cities, which equates to hundreds of millions of photos, making it possibly the largest collection of images of homes in the world today. When a guest decides to select a home, one of the biggest influences in their decision is a diverse set of images. But a lot of times hosts will take a lot of pictures of a single room and forget to take pictures of the other rooms.
They also have the option to add captions, but a lot of cases they're totally off.
We were faced with a challenge of identifying what's actually in these pictures and present them properly on the site. That's one area where machine learning excels. But the real challenge was one of scale. We had upwards of 500 million images to get through. It was going to take months to really go through all of these.
Using TensorFlow, we were able to speed up the process and deliver a reasonable model within days. BigHead is Airbnb's machine learning platform. We had the idea of making it very agnostic to different ML frameworks, and so we leveraged TensorFlow to train the model, and then BigHead helps with the model lifecycle, the feature management, and then TensorFlow serving to help serve the model results.
Before you think about which tool to use, you first think about which model to use, right? And we did research on this. We find that ResNet 50 was one of the state-of-the-art performing models. We used that as the basic architecture.
We used TensorFlow's Keras APIs and serving and some of the distributed GPU computations. This ultimately led to a pipeline that we could deploy to go through hundreds of millions of images very quickly.
So the end goal is basically using these classifications of images to make sure that their first initial set of photos that they see aren't just a picture of the garage and bathroom, but it could be of the living room that's gorgeous, in the bedroom, in the swimming pool. Future applications could be to detect different objects in homes, and if users decide to search on the website for specific amenity types, we can actually bubble that up to the surface.
If you like how Airbnb operates today, the reason was because of machine learning, because machine learning is almost everywhere in the company. Search ranking, pricing, predicting booking.
We're passing into the hundreds of models, so it's something I expect to keep growing.
And with a lot of these new frameworks coming out, we can make better experiences for our guests and better business decisions as well.
Good afternoon. I'd like to welcome you to TensorFlow Model Optimization, Quantization, and Pruning. It's a talk given by my colleague at Google, Rafael Alvarez.
Hi. Is this? Okay, there you go. Hi, my name is Raziel. I lead TensorFlow Model Optimization, and today I will talk about our toolkit and in particular about techniques around quantization and neural connection pruning. Yeah. So first I'll introduce what is model optimization, what is our toolkit, and then reason about why we think it's important, why we're investing in this area. Then I'll cover the tools that we have available. And at the end, I will give an overview, a quick overview on about our roadmap for the short term or in the longer term. And hopefully at the end of the presentation, we still have some minutes to go over a Q&A. So our toolkit implements techniques that should allow you to optimize machine learning models for deployment and execution. We think this is important because machine learning is everywhere, right? It's a very important field, and we think that there is a lot of room to make it more efficient, and this has some implications, both like economy, like you can make all these applications much better, right? Like the quality, or cheaper to execute. But also we can enable some new models and new deployments and new products that otherwise are not possible, even if you just try to do execute these machine learning models on servers, right? So currently machine learning runs either on the server or on the edge. On the server, you may think that there is a lot of capacity, there is a lot of compute and memory. So what is the benefit of optimizing these models? Well, applications are still bound by latency. There is still a very important metric for a lot of applications. Or you want to improve the throughput, right? How many tasks can run on your server. And these two are also directly correlated to money, right? So everybody will want to save money, and potentially we're talking a lot of money. Now, on the edge is a little bit more obvious why we need optimization, right? It's a very resource-constrained environment, even if you're talking about applications in general. We need to deal with, reduced memory, compute, power consumption is typically an issue. Bandwidth, both downloading models from the cloud or even within the chips to be able to transfer parameters from memory to the processor. This could be a problem if the model is too large. Plus, we have a wide variety of hardware, more than in the server, and we need to make sure that these models run efficiently on all these different types of hardware. So it follows that if we are optimizing these models, then we can have better models, and then eventually it starts translating in enabling new products that otherwise couldn't exist if we just were running these models on a server. And this opportunity is larger than just on smartphones. Machine learning is it's trickling down into more environments. We have machine learning models, for example, that are used to detect failures in machinery in factories, or we use it in self-driving cars. We use it in the office to scan documents and try to understand them. And just to give you some numbers, right? Like the size of the smartphone market is really a fraction of the potential for the edge devices in general. So basically, the two reasons is we want to make machine learning more efficient. It's already very important for the servers, but it's pretty crucial for embedded devices. So we started this toolkit about a year ago. We initially launched post-training quantization with this hybrid type of quantization, and I'll go in more detail later in the presentation. Then earlier this year, we launched the API for neural connection pruning. Then we created this specification of quantized operations, integer quantized operations for TensorFlow Lite. and we launch also post-training quantization support targeting this specification. More recently, we added support for reduced float precision, and hopefully soon we're going to be launching quantization-aware training API, and also adding support to TF-Lite for sparse computation. So now I'll go into these techniques and these tools in a little bit more detail. So let's start with quantization. But first, I think it's important if we have some at least basic understanding of what is quantization and why it's hard, and why we are approaching our tools the way that we're doing it. So let's start with a simple example. Matrix multiply, it's a basic operation for machine learning models. Right, you have two matrices, two tensors, A and B, and then you do some multiplication, accumulation, and you get a third tensor C. Right? So each tensor is just a bunch of values that produce the third tensor. Then just a little reminder about how matrix multiply works. So each one of these results of the tensor C are computed as multiplications and accumulations. So if we look at one of them, then if we think how we're training these models, typically in a higher precision, let's say float 32, then it follows that the operands of the multiplications are float 32 in precision, and then the product will be also a float 32, right? And then the accumulation will be also float 32. So this is fairly straightforward. There is some loss in precision, but machine learning is pretty good at dealing with it, at least at this level of precision, so no problem. Now, what does this have to do with quantization? Well, let's go back to what were our goals for optimization, right? We want to be able to address all these restrictions. And also, we want to be able to deploy in as much hardware as possible. So a common thing that we do is let's reduce the precision that we operate in. Right? Let's say, for example, go from the 32-bit floats to 8-bit integers, and then let's operate, let's say, entirely with integer operations. And this will be good because then, we are going from 32 bits to 8 bits, so we reduce the memory. The models are 4 times smaller. Then integer operations are typically faster to execute. Then they are also consume less power. And then because the parameters and also the dynamic values, the activations are smaller, then we reduce bandwidth pressure, right? It means that in the pipes and the chips, then there is more room for things to flow around, which can also translate in faster compute, reduced power. And then integer operations tend to be a fairly common denominator across hardware, right? CPUs, DSPs, different APUs, they support the integer operations. So, okay, so we said we're going to reduce the precision. So how do we convert the 32-bit float to 8-bit integers? Well, we do something right now. We do something very simple, right? So we have this linear mapping where we say, okay, we take the values from a tensor, we compute the minimum and the maximum value, and then based on that, we spread them evenly on the 8-bit range. Basically, it's very simple, right? So is that all that we need to do? Well, I wish. So it's not that simple, right? So let's go back to the example. So we have the matrix multiply, and now let's say that we quantize the values, right? And they are already 8-bit integers. So the operands in the multiplies are 8-bit integers, and then the multiplication, the products. Now you need 16-bit to represent it. And then you need to accumulate, and you probably want 32 bits to accumulate on that, right? So what is the problem? Well, the problem is that now you have tensor C full of 32-bit values, and that is not great when you want to fit that into another matrix multiply that you really want to execute this as 8-bit integers, because we already talked that it's so efficient, right? So what do you do? So you scale them back down, right? So you just sort of quantize them on the fly now, back down to 8-bit integers. So then you can feed them to your 8-bit matrix multiply and all good. But what are the implications of all this process? Well, so it means that we're changing the static values, right, the parameters, the weights. We are changing also the dynamic values, the activations, because we're scaling them, quantizing them on the fly. And it also means that we are changing the computation, right? In this case, very simple example, we just had a scaling operation, but it can be a bit more involved. So you could say, okay, that doesn't seem that hard, right? Like we just added another scaling operation, and it's just easy, right? Well, some math is a little bit more complicated than that. This example actually is from layer normalization of an LSTM. And this one, aside from looking a bit more complex, is it's an example where if you just apply these naive rules of operate, rescale, you actually end up in sort of a numeric black hole where scales cancel each other, and basically just things don't work if you just go naively about it. And then it's more complicated because in your decisions about how you're gonna represent this computation in integer form, quantization, we want to be efficient, so lower precision is good, but we also want to be accurate, which means lower precision is bad. So it's a lot of trade-offs that you have to do. Then further complicating things is we have heterogeneous hardware, right? There is all different types of hardware with different capabilities, right? Different operations that each hardware supports, and also different preferences. Some hardware is, better executing, operations, say, in reduced float, or with different bit widths or different restrictions. So, and we want to account for all those things when we are creating our quantized recipe or quantized program. Then there is the fact that machine learning, is hard to interpret. We don't understand it, right? Like we don't understand how it works. Not to the level that we can have good proofs to know that a transformation that we're doing to this model, to this program, will actually work or not result in a catastrophic error, right? You don't want to take a model, you quantize it, and then this model suddenly starts giving you some weird results. So it makes it a little bit much more complicated to define these transformations. And then finally, I will say that this is all more complicated because the model is not enough, the program is not enough. Depending on how the quantization is defined, you might also need some extra data. So in the example of the matrix multiplier, right, we needed to compute the minimum and maximum values of the dynamic activations, right? And that only can be done if we run inferences through the model, right? Which means that you need to provide some representative data. So basically, it's just another hurdle that you have to account when quantizing these programs. So, basically this means that when we talk about quantization, we're really talking about rewriting, transforming this machine learning program to an approximated representation based on the operations that you have available. So now, how are we addressing this in our toolkit? Well, the first thing that we decided to do was try to scope down the problem and say, okay, we're going to define the specifications that for common operations, like in this case is a diagram for a convolution, have a well-defined quantization behavior, right? So we know that now with this information, this low-level information that is relevant to quantization, then hardware can target those specifications, and then our tools can target that specification. And then we can all work at this level. And then we also get the other benefit that from the user point of view, you can quantize a model, and then this model can run in different hardware without any change. So right now, in our toolkit, we support 3 different quantization types. I'm including here reduced float as a quantization type, but it's just a much simpler thing where we just typically go from float 32 to float 16 parameters and computation. So that's pretty straightforward. The next one is our hybrid quantization, which basically makes use of 8-bit for the parameters, biases and activations. We leave as 32-bit floats. And then we try to be as smart as possible for how we execute this program. So the goal being that, for example, heavy operations like big matrix multiplies are left in the integer domain, and then we use floating point for things like activation functions. So it's a nice trade-off between accuracy and performance and optimizations. Then the third one is integer quantization. This means everything is integers. All the parameters are integers, and all the operations are integers. This is obviously the more complicated one. So the benefits of the reduced float is, well, you guess your models are now half size. And then depending on the hardware support, you might get some speed ups. And then the accuracy losses tend to be very minimal. Pretty much always works. I haven't seen myself, at least, an actual model that doesn't work in Float 16 that was trained in Float 32. Hybrid quantization then pushes it further. You now get 4x reduced in size, and then depending on the computations, the operations that you are using, you may get different performance improvements. It tends to be larger for fully connected models or RNNs. And then the third one is the only integer quantization, so it has the same benefits as hybrid in terms of memory size, but is faster to execute. And it has a great advantage that it has more hardware coverage. So for example, typically MPUs, some of them are only like integer based, like our HTPU. Now, let's talk about the tools to actually quantize those models based on those quantization types. So we have two types of tools. One that works post-training, so it works directly on the trained model, and the other one that is work in progress is during training. So let's talk about the post-training. The process is very simple. You basically assume that you just have a trained model. It doesn't really care how you train it. You just have a TensorFlow model. Then currently via the TensorFlow Lite converter, you just convert this model to TensorFlow Lite and quantize it on the fly. And then you just have a model that you can execute on whatever hardware is supported in that quantization type. So now let's look at the specific quantization types. So the first one, reduced float, is you just set a couple of flags. You just say, use the default optimizations, and then the type that I am targeting is float 16. And then basically this will take care of changing all the parameters and the computation. And again, depending on the hardware that you're running this model, you might get a speed up right now. For example, GPUs support float 16 natively, so you might get some speed up there, either because of the computation or even just because of the bandwidth in your chip will be reduced. Like I said, benefits, well, the size goes to half, and the accuracy drop is very minimal. It's, I will say, within the noise. Then the next one is our hybrid quantization. So again, this is very easy. You just set the flag now. This is the default for the TensorFlow Lite converter. You set it to default. And then, again, it will make sure to quantize all the parameters. And then operations that doesn't have yet a defined specification for the quantized form, it will be kept in the original precision. And then you will get some speed ups, and you will be able to execute in whatever hardware complies with that specification. So typically this one works pretty well for CPUs. And again, benefits, 4x compression for the models. And then you get some speed ups. All these are convolution-based models, so that's why the speed up is not as big. And I would say these are 1-year-old numbers, so probably right now is faster. And The same for accuracy. So accuracy is pretty good, and actually that's we're working on some changes. So for convolution models, it will even be a bit more accurate soon. Then the third one is the integer quantization, right? So this one is the one that is a bit more complex because now you need to provide some data, right? So you say, okay, I want to optimize a model, but I want to use the integer quantization. So now you need to provide some data. And by data, I mean unlabeled samples of what your neural network will typically see in reality, right? So if it's an image processing model, you need to feed some pre-processed images. And we're not talking about a lot of data for the results that I'm going to show next. We're just talking about 100 samples. That works pretty well. So it's a bit more complicated, but it's not very complicated. So these are some results from post-training quantization across different models. As you see, for the majority of models, the loss is not that big with respect to the full precision train baseline. The only one I will say is the mobile SSD model. So that is a bit more meaningful drop. But again, a variety of models work pretty well with post-training quantization. Now I'll talk about during training because, like I showed in the previous results, there is still some models that will benefit from doing this training, quantization-aware training. And by quantization-aware training, we mean we try to emulate the quantization operations, the quantization losses during the forward pass of the neural network with the hope that the parameters will be tuned to account for that. So the process for doing the quantization-aware training for using our API, it's a little bit more involved, but we are, again, trying to make it very simple. So we build this API in Keras, again, to make it very easy to use. So basically, we assume that you already have a Keras model, and then you just need to call our API to apply the quantization. So, and this might change a little bit, but it will look something like this. So you just have a model that you already built using Keras layers, and why not? And then the only thing that you need to do is call our API on your model. Then you get now a model that is rewritten to have all the emulation of quantization. And then you just call your fit function. And that's it. So then you just train your model as usual. And then you can go through the TensorFlow Lite converter, and then it will take this model that was trained with quantization. It will have all the data necessary to quantize it, and then it will produce a quantized model that now, just like the post-trained model, you will be able to execute in different hardware. These are some numbers from quantization-aware training, preliminary numbers. If you see the delta is a little bit better than post-training quantization, it's not a very big difference except for the mobile SSD. So before it was 4% for post-training quantization. In this case, it's 2.9%. So quantization-aware training is still a useful tool. That's why we're building it. Now you may wonder, those were a lot of quantization types and tools. So which one should I use? So my recommendation is, if you are just starting, just start with try reduce float. That's the first one to try. It's just very easy to use. It doesn't require any data. The accuracy will probably be the same. And then latency, depending on the hardware, you might get some benefits, reduced latency. And then compatibility, basically everywhere you can execute floating point operations, you will be able to use it. The next thing to try will be the hybrid quantization. Again, there is no data requirements. The accuracy will be still good, probably not as good as float 16 in some cases, but it's still good. It will be faster than the reduced float. And basically, compatibility, well, everywhere that you have support for float and integer operations. Then the third one to try is the integer quantization with the post-training tool. So this one is a bit more complicated just because you need to provide a little bit of data. The accuracy will be worse or the same as hybrid, but the latency, this will be the fastest. and then it will also give you more hardware coverage. And then the last thing to try will be the integer quantization with quantization aware training soon. And basically this is, there. This will be a little bit more involved because now you're doing training. You're supposed to have now a training setup, a training script, but the accuracy will be better than doing just the post-training version. And again, you get the benefits of being the fastest one and the one with more hardware coverage. So that was quantization. And again, all these tools we're trying to make it very easy to use, so it would be great if you try them out and give us some feedback. Then connection pruning. So what is neural connection pruning? Well, the way that we have implemented it so far, it means it's a training time technique that during the training process, it will start dropping connections from the neural network. And then these connections the drop connections basically just become zeros in the tensors that you're training, and then that means that you end up with sparse tensors. Now sparse tensors are great because you can compress them and potentially execute them faster. So this is an example. This is say a tensor, how it starts randomly initialized. The dark values means values that are non-zero, and white means that values that are zero. And then as the training progresses, then it starts becoming sparser and sparser. And if you see this tensor is basically we're removing most of the parameters there. The process for the API is very similar to the quantization aware training API. Again, we're trying to bring some consistency to our APIs. So it's built on Keras. So it assumes that you have a model that is trainable on Keras, and then you're going to call our API to apply the pruning logic. And this, again, we're trying to make this as simple as possible. So the only thing that you need to define is the pruning schedule. Basically, when you want to start dropping these connections and until when and how fast, how aggressive you want this pruning to be. And then you just call our prune function, which again will modify your graph to add all the pruning operations internally. And then you just call your fit function and you train as usual. So basically you train as usual, and then once you train, you have two options now, or soon you will have two options. You can just take the save model, the TensorFlow save model, you can just compress it, gzip, and then the model will be smaller. And soon you will be able to convert it via TensorFlow Lite, and you will get also reduction in size and potentially some speed ups, depending on what prune configuration you're using and the hardware that you're targeting. So this should be done pretty soon. Now, what are the benefits of pruning? We've tried in a lot of tasks, like really a lot of tasks on image, speech, audio, and it worked pretty well. And like a lot of techniques that require a lot of hyperparameter tuning and careful restarting your models and things like that. But pruning has worked pretty well without a lot of babysitting. Then it has potential for speed ups depending on hardware support. And we also have pretty good results. Like we can make a lot of the parameters basically go away. We see 50 to 90% with negligible accuracy loss. And the other great thing is that it works well also with quantization. So a typical setup that we've tried is we train in pruning, and then we use post-training quantization. And basically, the accuracy is pretty good, and you get the compound benefits of both techniques. These are some older now results that we have when we launched this. So, I mean, this is an Inception B3. You see, we can get all the way almost to 90% sparsity with relatively small accuracy losses. And the other GNMT is neural machine translation, where again, we can take it to almost 90% pruning and also small accuracy losses. And we've done this for example, speech recognition. We actually had recently the Google Pixel event where the speech recognition models there use pruning and quantization, and we're able to have a model with server-side quality running on a phone, which is pretty good. Okay, so now I'll finally cover just real quick our roadmap. Like I mentioned, quantization, we're working on quantization training API, so that should be ready soon. And we are also working on our specs for quantizing RNNs, which are typically trickier to quantize, like LSTMs. Then I didn't include it there, but we're making some improvements to the hybrid quantization to be more accurate, particularly for convolution layers. And then for sparsity, we're adding support for sparse computation in TensorFlow runtime. Longer term, I don't know if you have heard about MLIR, but it's state-of-the-art compiler infrastructure. But this is particularly interesting to us because it's a better way for us to write these transformations. And at the end, like I said at the beginning of the talk, we're taking a model, we're transforming it into one program into another representation of that program. And some of the things that we want to enable is better target hardware. So our specifications are great because users can target our specification and execute in different hardware, but some users just want to zero out in one hardware and get the best out of it. So we're hoping that with the new infrastructure that we're building on top of MLIR, this should be possible. And finally, I really just want to encourage you to try it out and give us feedback. What techniques you would like to see? Research is, there is techniques popping up all over the place, and a lot of the work that we have to go through is calling what's useful and what's not, what is general and what is very specific. So we would love to hear your feedback about that, and also about the tools that we already have there in the toolkit. We're trying to make them as easy as possible to use. We know that we still have a long way to go, but any feedback that you can provide will be really, really appreciated. And I think there is a little bit of time for questions, if any of you have questions. Okay. Thanks.
Hi, thank you for the presentation. I have a question regarding the training with integer quantizations. In the pipeline, is that going to be true quantization during training, or?
No, so right now the way, and by true I mean that you expect that all the operation happens in the integer domain.
Yes, yeah.
Not right now. That's something I really want to enable because I want to make training faster as well. But right now, the way that we are targeting is, I don't know if you're familiar with TensorFlow APIs, but we have this low-level API, unfortunately called fake quantization, that basically just emulates these losses. And that one is still basically what we do there is we quantize parameters, and then we dequantize them, and then we do the float operation. So that's what we are using right now. But yeah, longer term, we want to do true integer forward passes.
Thank you.
Hi. Can I go? Oh, I have this one question.
Oh.
So after you do the quantization, is there a way that you can also visualize, the finished quantized model? It was one question, and I had another question. Let me think about it. But is there a way that you can also, the other question was, what sort of tools are you going to provide as far as to sort of do like model correctness, and at least evaluate, how, whether this quantized model is sort of like functionally correct in a sense?
Yeah, so for visualization, again, it depends where, but for TensorFlow Lite, we have a visualizer so you can see the quantized model. I don't know if it will give you a lot of information depending what you're looking for. We also want to make our tooling a bit better because perhaps for whatever reason you want to get all researchy and start looking at the activations and how they change.
Sure, yeah. If there's like inserted ops and so forth,
yeah,
I
so
can probably evaluate
for sure
that.
with the TF Lite visualizer, you can see how the graph changed. So the second question about correctness is really tricky because in my experience, the only thing that really works is to really evaluate on the real data that you care to run your model on. Yeah, we try to do things like L2 norms to approximate, versus the full precision one versus the quantized one. And it gives you a sense of, maybe some really catastrophic numerical errors, but otherwise is really just a guess, right?
That's
particularly depending on the output layers. Categories are easier to quantize because the error is not very meaningful as long as you get the right category. Regressions are much harder because now you really care about the actual value. So it's an open problem.
It's a tough problem, yeah. Thank you.
I have a question about the results from the GNMT training with induced sparsity. I was wondering if you had any insights on why the training with 80% sparsity would perform better than the original version? Like if you looked at the...
the hand-wavy thing that we always say in these cases is some regularization happened. And yeah, and I've seen the same with some quantized models. I've never had the year to really sit down and try to understand what the reasons are for all this. Sometimes it's just because it's within the noise, right? It all depends on your evaluation set, right? If it's really not that big or not that meaningful, then these jumps are all possible. Like I've seen some models where, it looks great after you quantize it, then you throw in a new data set, say from speech recognition and noisier utterances, and then you clearly see the difference between one and the other. So it's a lot of it can be just noise.
Hi, you mentioned explainability, and a technique could be like saliency maps. Do you have any insights on how these techniques affect the ability to calculate the gradients, to calculate the saliency maps, for example?
That's something that we want to invest more, and we haven't had that much time to do it, and I would love to, for research to get more excited that are trying to understand neural networks, to also understand neural networks that have been approximated, but so far I haven't gotten any luck trying to get the people on that side excited about it. But yeah, I really don't have any meaningful thing to say because I haven't run many experiments around it.
Thank you.
Yes, sir.
Hey.
Hey. Sorry.
Yeah. So what is the best way to handle fragmentation of hardware? So like quantization can depend on the target hardware. And more often than not in mobile phones like Android, you have so many types of hardware. So what are the best practices there?
Well, so one way that we tried to do it was, again, with these specifications. And I don't know to what extent it makes our hardware partners happy because we would like to be able to target their hardware in the most precise and efficient way, but that's one way that we try to address it, right? Like if, with our knowledge of somewhat what the hardware is there and what it supports, we try to create these specifications that try to accommodate for everybody, which again, it's good and at the same time it's bad. Then longer term, and again, I don't want to say too much because I don't have a very concrete plan to share, but part of what we're building with the MLI infrastructure is we want to be able to better target that hardware, better partner with hardware vendors to understand what are the hardware capabilities and better create these transformations that target that hardware. But we're really trying to make it much better.
So for now, does it mean like you go with the lowest common denominator, maybe like F316? Like imagine an Android app that you have to deploy on a lot of things. So.
And that's why we have all these different quantization types, right? Like we have 3 types, right? And soon, hopefully, we'll be able to even just mix and match those different types because, at the end of the day, it's a very arbitrary boundary. Then we say, this is all integer quantized, and this one is hybrid. In the reality, we should be able to take advantage of mixing and matching of precisions to get something better.
Thank you.
I have a question about pruning.
Yeah.
As a general rule on layers, operations are converted to matrix multiply because of their efficiency. With pruning, you're now passing in individual multiply operations one by one. There must be some crossover point at which you need to prune by 10, 15, 20% before you're crossing over and actually get an improvement. Thoughts on where that is?
So, and I don't know if this is exactly what you're asking, but so for example, our pruning API supports you specifying what the pruning structure is. So for example, we know that for CPUs, SIMD instructions, we typically have registers that can accommodate 16 values. So we know that if we want to speed it up on CPU, we expect you to provide or to set the setting to say, oh, I want to prune in blocks of say 1 by 16, and that's how we can get speed ups on CPU, for example. And unfortunately, right now probably it's going to be like hardware dependent, but that's one thing that you can do right now.
Right, but is there some sort of minimum?
We're out of time.
Oh,
I'm sorry. I'm sure you all can talk.
We can talk
after.
about it afterwards.
Thank you all so much for coming, and thank you.
Airbnb is an online marketplace. We have over 5 million different homes in 81,000 cities, which equates to hundreds of millions of photos, making it possibly the largest collection of images of homes in the world today. When a guest decides to select a home, one of the biggest influences in their decision is a diverse set of images. But a lot of times hosts will take a lot of pictures of a single room and forget to take pictures of the other rooms.
They also have the option to add captions, but a lot of cases they're totally off.
We were faced with a challenge of identifying what's actually in these pictures and present them properly on the site. That's one area where machine learning excels. But the real challenge was one of scale. We had upwards of 500 million images to get through. It was going to take months to really go through all of these.
Using TensorFlow, we were able to speed up the process and deliver a reasonable model within days. BigHead is Airbnb's machine learning platform. We had the idea of making it very agnostic to different ML frameworks, and so we leveraged TensorFlow to train the model, and then BigHead helps with the model lifecycle, the feature management, and then TensorFlow serving to help serve the model results.
Before you think about which tool to use, you first think about which model to use, right? And we did research on this. We find that ResNet 50 was one of the state-of-the-art performing models. We used that as the basic architecture.
We used TensorFlow's Keras APIs and serving and some of the distributed GPU computations. This ultimately led to a pipeline that we could deploy to go through hundreds of millions of images very quickly.
So the end goal is basically using these classifications of images to make sure that their first initial set of photos that they see aren't just a picture of the garage and bathroom, but it could be of the living room that's gorgeous, in the bedroom, and the swimming pool. Future applications could be to detect different objects in homes, and if users decide to search on the website for specific amenity types, we can actually bubble that up to the surface.
If you like how Airbnb operates today, the reason was because of machine learning, because machine learning is almost everywhere in the company. Search ranking, pricing, predictive booking.
We're passing into the hundreds of models, so it's something I expect to keep growing.
And with a lot of these new frameworks coming out, we can make better experiences for our guests and better business decisions as well.
You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code? Predict the y when x equals 10. You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you. Hi everyone, and welcome to episode 2 of TensorFlow Zero to Hero. In the last episode, you learned about machine learning and how it works. You saw a simple example of matching numbers to each other and how, using Python code, a computer could learn, through trial and error, what the relationship between the numbers was. In this episode, you're going to take it a little further by teaching a computer how to see and recognize different objects. For example, look at these pictures. How many shoes do you see? You might say 2, right? But how do you know they are shoes? Imagine if somebody had never seen shoes before. How would you tell them that despite the great difference between the high heel and the sports shoe, they're still both shoes? Maybe they would think, if it's red, it's a shoe, because all they've seen are these two and they're both red. But of course, it's not that simple. But how do you know that these two are shoes? Because in your life, you've seen lots of shoes and you've learned to understand what makes a shoe a shoe. So it follows logically that if we show a computer lots of shoes, it will be able to recognize what a shoe is. And that's where the dataset called FashionMNIST is useful. It has 70,000 images in 10 different categories, so there's 7,000 examples of each category, including shoes. Hopefully, seeing 7,000 shoes is enough for a computer to learn what a shoe looks like. The images in FashionMNIST are only 28 by 28 pixels, so they're pretty small. And the less data used, the faster it is for a computer to process it. That being said, they still lead to recognizable items of clothing. In this case, you can still see that it's a shoe. In the next few minutes, I'll show you the code that will teach you how to train a computer to recognize items of clothing based on this training data. The type of code you write is almost identical to what you did in the last video. That's part of the power of TensorFlow that allows you to design neural networks for a variety of tasks with a consistent programming API. We'll start by loading the data. The FashionMNIST dataset is built into TensorFlow, so it's easy to load it with code like this. The training images is a set of 60,000 images, like our ankle boot here. The other 10,000 are a test set that we can use to check to see how well our neural network performs. We'll see them later. The label is a number indicating the class of that type of clothing. So in this case, the number 9 indicates an ankle boot. Why do you think it would be a number and not just the text ankle boot? There's 2 main reasons. First, computers deal better with numbers. But perhaps more importantly, there's the issue of bias. If we label it as ankle boot, we're already showing a bias towards the English language. So by using a number, you can point to a text description in any language as shown here. Can you guess all the languages that we used here? When looking at a neural network design, it's always good to explore the input values and the output values first. Here we can see that our neural network is a little more complex than the one in the first episode. Our first layer has the input of shape 28 by 28, which, if you remember, was the size of our image. Our last layer is 10, which, if you remember, is the number of different items of clothing represented in our dataset. So our neural network will kind of act like a filter, which takes in a 28 by 28 set of pixels and outputs one of 10 values. So what about this number, 128? What does that do? Well, think of it like this. We're going to have 128 functions, each one of which has parameters inside of it. Let's call these F0 through F127. What we want is that when the pixels of the shoe get fed into them, one by one, that the combination of all of these functions will output the correct value, in this case 9. In order to do that, the computer will need to figure out the parameters inside of these functions to get that result. And it will then extend this to all of the other items of clothing in the dataset. The logic is, once it has done this, then it should be able to recognize items of clothing. So if you remember from the last video, there's the optimizer function and the loss function. The neural network will be initialized with random values. The loss function will then measure how good or how bad the results were, and then with the optimizer, it will generate new parameters for the functions to see if it can do better. You've probably also wondered about these, and they're called activation functions. The first one is on the layer of 128 functions, and it's called ReLU, or Rectified Linear Unit. What it really does is as simple as returning a value if it's greater than 0. So if that function had 0 or less as output, it just gets filtered out. And softmax has the effect of picking the biggest number in a set. The output layer in this neural network has 10 items in it, representing the probability that we're looking at that specific item of clothing. So in this case, it has a high probability that it's item 9, which is our ankle boot. So instead of searching through to find the largest, what softmax does is it sets it to 1 and the rest to 0, so all we have to do is find the 1. Training is then very simple. We fit the training images to the training labels. This time we'll try it for just 5 epochs. Remember earlier we had 10,000 images and labels that we didn't train with? These are images that the model hasn't previously seen, so we can use them to test how well our model performs. We can do that test by passing them to the evaluate method like this. And then finally, we can get predictions back for new images by calling model.predict like this. And that's all it takes to teach a computer how to see and recognize images. You can try this out for yourself in the notebook that I've linked in the description below. Having gone through this, you've probably seen one drawback, and that's the fact that the images are always 28 by 28 grayscale with the item of clothing centered. So what if it's just a normal photograph and we want to recognize its contents, and you don't have the luxury of it being the only thing in the picture as well as being centered? That's where the process of spotting features becomes useful, and the tool of convolutional neural networks is your friend. You'll learn all about that in the next video, so don't forget to hit that subscribe button, and I'll see you there.
with us through those technical difficulties, but it is my great pleasure to bring up two of my colleagues at the TensorFlow team at Google. We have Brajesh and Kangi, who will talk to you about TensorFlow.js.
Thank you. Hello, everyone. Again, thank you for your patience. We are super excited to be here and talking to you about TensorFlow.js and how to bring machine learning to JavaScript applications. My name is Brajesh. I'm a technical program manager on the Google TensorFlow team. And here's my colleague, Kangi, who's a software engineer on the TensorFlow team. So here is an outline of what we are going to cover in this talk. We will start with the what and why of TensorFlow.js. We will see some of the ready-to-use models that TFJS supports. We will do a code walkthrough of the development workflow, both to use one of these pre-trained models as well as training a custom model. We will delve a little deeper into the tech stack and the roadmap. We will show you what the community is building with TensorFlow.js. There are some very impactful applications that are being built, and we'd love to show you some examples. And finally, we'll point to some resources that you can start exploring. All right, so we have a lot of exciting content to cover, so let's get started. You may have heard at the TensorFlow.js keynote an overview of the technology today morning. We are going to build on that here. But first, a quick recap of the basics of TensorFlow.js. So in a nutshell, TensorFlow.js is a library for machine learning in JavaScript. It is built for JavaScript developers to create and run machine learning models with an intuitive JavaScript-friendly API. This means you can use it to perform training and inference in the browser, browser-based platforms, and in Node.js. ML operations are GPU accelerated, and the library is fully open source, and anyone is welcome to contribute. Okay, so TensorFlow.js provides multiple starting points for your needs, right? So you can use the library. You can directly use off-the-shelf models that the library provides, and we will see a lot of these in a bit. You can also use your existing Python TensorFlow models with or without conversion, depending on the platform that you're running on. Or you can retrain an existing model with transfer learning and then customize it to your data sets. That's the second starting point. Transfer learning typically needs a smaller data set for retraining, so that might fit your needs better. And the third starting point is you can build your model entirely from scratch with a Keras-like layers API and train it. You can train it either in the browser or on server with Node.js. So we are going to delve much deeper into some of these workflows today. JavaScript, of course, is a ubiquitous language. So by virtue of that, TensorFlow.js works on a variety of platforms. It lets you write ML code once and run it on multiple surfaces. As you can see, the library runs on any standard browser, so regular web apps, progressive web apps are covered. On mobile, TFJS is integrated with mini app platforms like WeChat. We have just added first-class support for the React Native framework, so apps can seamlessly integrate with TensorFlow.js. On server, TFJS runs on Node. In addition, it can run on desktop applications using the Electron framework. All right, so why TensorFlow.js? Why run ML in the browser? Right, so we believe there are compelling reasons to run ML on a browser client, especially for model inferencing. Let's look at some of these reasons. Firstly, there are no drivers and nothing to install. You include the TensorFlow.js library, either at page load time by script sourcing it into your HTML page, or by bundling with a package manager into your client app, and you're good to go. That's it. The second advantage is you can utilize a variety of device inputs and sensors using standard device API, such as camera, microphone, GPS, through standard web API, HTML API, and through a simplified set of TF data API. And we are going to see some examples today. TFJS lets you process data entirely on the client, which means It's a great choice for privacy-sensitive applications. It avoids round-trip latency to the server. It is also WebGL accelerated. So these factors in combination, combine to make for a more fluid and interactive user experience. Also, running ML on the client helps reduce server-side costs and simplify your serving infrastructure. For example, no online ML serving that needs to scale to increasing traffic and so forth is needed because you're offloading all your compute to the client. You just host a ML model from a static file location, and that's it. On the server, there are also benefits to integrating TensorFlow.js into your Node.js environment. Right? If you are using a Node.js serving stack, it lets you bring ML into the stack as opposed to calling out to a Python-based stack. So it lets you unify your serving stack all in Node.js if you're using Node.js. You can also use your existing core TensorFlow models to bring them into Node.js, not just the pre-built off-the-shelf models, but rather your custom models that were built with Python TensorFlow can be converted, and in an upcoming release, you don't even need the conversion process. You can just use them directly in Node. And finally, you can do all of this without sacrificing performance. You get CPU and GPU acceleration with the underlying TensorFlow C library because that's what Node uses. And we are also working on GPU acceleration via OpenGL. So that removes the need for depending on CUDA drivers as well. So effectively, you get performance that's similar to the Python library. So these attributes of the library enable a variety of use cases across the client-server spectrum. So let's take a look at some of those. So on the client side, it enables you to build features that need high interactivity, like augmented reality applications, gesture-based interaction, speech recognition, accessibility, and so forth. Right? On the server side of the spectrum, it lets you have your more traditional ML pipelines that solve enterprise-like use cases. And in the middle, that can live either on the server or on the client, are applications that do sentiment analysis, toxicity and abuse detection, conversational AI, ML-assisted content authoring, and so forth. So you get the flexibility of choosing where you want your ML to run, on the client, on the server, either or. So whatever your use case is, TensorFlow.js is production ready to be leveraged. So with that intro, I'd like to delve deeper into the ready-to-use models available in TensorFlow.js. Our collection of models have grown and is growing to address the use cases that we just mentioned, namely image classification for classifying whole images, detecting and segmenting objects and object boundaries, detecting the human body and estimating pose, recognizing speech commands and common words from audio data, and text models for text classification, toxicity, sentiment detection. You can explore all of these models today on GitHub. You can use them by installing them with NPM or by directly including them from our hosted scripts. So let's dive into a few of these models and see more details on these. So this is the PostNet model. It performs pose estimation by detecting 17 landmark points on the human body. It supports both single person and multi-person detection within an image. Now there are multiple versions of this model, versions that are backed by MobileNet and those backed by ResNet, that provide options for balancing accuracy versus model size versus latency, depending on your needs. And it enables use cases like gesture-based interaction, augmented reality, animation, and so on, things that are well served by running ML on the client. By the way, you can explore a demo of this particular model at our booth in the expo hall. Another human model is the BodyPix model. BodyPix enables person segmentation, again, both single and multiple persons in an image. It identifies 24 body parts such as left arm, right arm, torso, left-right legs, and so forth. It also provides convenience API to segment and mask each body part in a different color, which is what you're seeing in this particular GIF. And in terms of use cases, you can be used for things like blurring faces in an image or blur the background, say to protect privacy. The COCO SSD object detection model enables object detection of multiple objects in an image. It detects about 90 classes defined in the COCO dataset. And the nice thing is it takes as input any browser-based image element, like an image or video or a canvas element, and returns an array of bounding boxes with the detected class and a confidence level. In this sample image, you can see that the kite is detected with a high confidence score, and you get a bounding box. There is also a deep lab model which offers semantic segmentation that's coming soon, yet to be released. So what I'd like to show you here is how easy it is to use a model like that, like COCO SSD, in your JavaScript app without dealing with tensors, transformations, or layers. And this pattern really applies to any of our pre-built models. Right, so first, you script source the library in your HTML file from the hosted CDN. Alternatively, you can just npm install the library and use a build tool like Webpack to bundle into a client.js file. Then you load the model. That's the .load method. And you call the model.detect method on the image element that you are trying to analyze. And that's it. What you get back is an array of objects that have the bounding boxes and the classes that are detected. So really, 4 or 5 lines of code to end up leveraging a powerful ML model in the browser. Text models are another useful set. TFJS has a toxicity detection model and a more general universal sentence encoder model. So let's look at the toxicity model a little closer. I want to show you a live example of this model in a web app. Give me a second. Okay, there you go. So here is a super simple web app that simply loads the model and passes a few sentences to it. And what the model does is classify it on a few dimensions, like does this signify an insult, is there a toxicity, is there a threat, and so forth. So let's try an example here. So I'm going to say something toxic. If I can see it, ignorance is pretty okay. So something that I would think is toxic. So that returns as toxic as well as returns as an insult. However, this model, I want to show you that this is context-based, not keyword-based. So you type the same word in a totally non-toxic context, you're going to see a different answer, and that's detected as not an insult. So this sort of model can be used on the client side in product reviews or in chat type of situations. Here is an example I want to show you from a Twilio developer who integrated TensorFlow.js into a chat app. And again, here it's able to detect that comments, toxic comments, and filter them right before sending. All right, so next slide. Another interesting model is face mesh. This model provides high resolution tracking of facial features. So it detects about 400 points on a person's face. So we believe that this model has great potential for real world applications. For example, detecting facial gestures, emotion, supporting richer accessibility features, and so forth. So now I'd like to show you a couple of cool demos built using FaceMesh. First up, and you might have seen this in the keynote session today morning if you attended. Here's an application built by one of our partner teams at Google. This app is called LipSync. This is a game that tracks how well you are lip syncing to a song, all real time in the browser. Right, so let's see a demo. Notice in particular how the display turns gray when the lip sync doesn't match the lyrics, and how the score kind of matches how well the person is lip syncing. All right. There you go. I'm going to move my mic closer. Okay, there's no audio here. Okay, we don't have audio, so but you can just sort of imagine, if you will. So when the lip syncing when the person is not lip syncing correctly, then there's feedback given back to the user, and this you can see is a type of example that one can build entirely on the client using this library, and sort of let your imagination go from there. So again, this is available at the TensorFlow.js booth. You're welcome to try and see how you do. The next application we'd like to highlight is a virtual makeup try-on app, again using FaceMesh. So this is a mini app that the company Modiface, which is a subsidiary of L'Oreal, has built on the popular WeChat platform. I would like to invite Brendan Duke from Modiface to come on stage and show you how they use TensorFlow.js to build this app.
Thank you. Thanks, Brajesh. So hi, I'm Brendan. I'm a research scientist at Modiface. And first, let me briefly introduce Modiface. So Modiface is an augmented reality for beauty company. It was founded in 2007 in Toronto, Canada, and acquired just last year 100% by L'Oreal. So today, Modiface collaborates with 20 beauty brand subsidiaries of L'Oreal, such as L'Oreal Paris, Maybelline. And you can find our technology in such online retail giants as Macy's, Sephora, or Amazon. So now I'm going to talk to you about how we make use of TensorFlow.js in our virtual try-on applications. So in order to introduce why we need a framework like TensorFlow.js, I'm going to use the WeChat mini program, for a makeup virtual try-on that we developed as an example to showcase the kind of challenges that you run into when you're deploying real-time virtual try-on systems. So first of all, we want to deploy our applications on the client side. This is for user privacy and to avoid the latency from doing a round trip to a backend server every frame. And also, we have a soft requirement of about at least 10 frame per second frame rate in order for our applications to feel interactive. So this is particularly difficult on the WeChat platform because you have to run your mini program in WeChat's JavaScript environment, and you inherit the limitations of JavaScript. So we needed both to develop a lightweight Spartan model for our face tracking, and also to find a framework that runs quickly in JavaScript, and ideally makes use of WebGL to run deep learning operators using the GPU hardware acceleration. So a second challenge we ran into is that the WeChat mini programs have a 2 megabyte cumulative file size. So we need to find a framework that's small and allows us to develop a small model, and so that we can load it as quickly as possible as well. And thirdly, because our models have some custom operators, we needed a framework that's extensible with custom operators. And we also needed a framework that is going to support all the different mobile phones that are supported by, mobile phone models that are supported by WeChat itself. So now I'm going to tell you about how TensorFlow.js fit the bill and was able to overcome some of these challenges that we ran into in deploying our Makeup virtual try-on. First of all, TensorFlow.js runs on the client side, and because it makes use of WebGL backend, it's able to harness the mobile phone GPU hardware acceleration, and which gives it like an order of magnitude speed up over browser-based CPU solutions such as WebAssembly, which are kind of limited right now by lack of SIMD and multi-threading. So TensorFlow.js really allowed us to hit our frame rate requirement. And second of all, the TensorFlow.js library is small and compact. We were able to package the library in about 700 kilobytes. And combined with our roughly 400 kilobyte model sizes, we were able to fit everything within the WeChat mini program file size limit. And thirdly, TensorFlow.js both has widespread support for built-in deep learning operators and also allowed us to extend it with our custom operators that we need for our face tracking. And finally, TensorFlow.js is supporting a wide variety of mobile phone models and has continuous support from the TensorFlow.js team. So for these 4 reasons, we chose TensorFlow.js as the framework to deploy our Makeup virtual try-on on the WeChat plugin. So now I'd like to share with you some of our results. So with the help of TensorFlow.js, we were able to successfully deploy to WeChat our easy-to-use real-time system for realistic AR virtual try-on of Makeup. Our entire final solution fit into about 1.8 megabytes. It's including the code and our models. And on an iPhone XS, our rendering and tracking together run at over 25 frames per second. So TensorFlow.js coupled with our TinyCNN face tracking model allowed us to deploy to web our fastest, smallest Makeup virtual try-on system to date. So now I'd like to briefly mention a few future research directions that we have going on at Modiface. So we've already used TensorFlow.js to create web application demos for our makeup try-on, our hair color try-on, and our nail polish try-on. And in particular for our hair color try-on, we were able to achieve an order of magnitude speed up on a guided filter operator that we use as a post-processing step by just taking our WebAssembly implementation of that operator and re-implementing it in TensorFlow.js. This amounted to about a 20 millisecond reduction in latency for the whole system. We also have a number of other research projects going on at Modiface, such as hairstyle transfer, virtual aging simulation, and skin analysis that we hope to use TensorFlow.js to deploy in the near future. So thank you everyone for listening, and I'll pass the presentation on to Kagi.
Thank you, Brandon. Hi, my name is Kang Yi. I'm a software engineer on the TensorFlow.js team. Next, I want to walk you through the workflow of developing apps with TensorFlow.js. We just saw the Modiface Lipsticks virtual try-on app, and I want to show you the details of building a sunglasses virtual try-on app, which uses augmented reality to allow users to try sunglasses through the camera in a web page. To build a sunglasses virtual try-on app, there are several components. First, we need a model that is trained to find the face. And second, the model needs to be loaded in the app to run inference. And third, the app needs to get video data from the camera, and some pre-processing is required so the video data is compatible with the model as input. And after the model inference, we need some post-processing to use the model output data. And finally, the sunglasses need to be rendered based on the model output. The first technical challenge is to get input data from the camera. TensorFlow.js provides a data API which enables developers to easily get data from a web camera, microphone, image, text, and CSV file. This data API will also prepare the data as tensor, so it's ready for the model with customized configurations. And the second technical challenge is to detect the face in the camera and find key points on the face. Previously, we have seen the face mesh model, which is pre-trained to identify up to 400 facial key points in 3D coordinates, and it is a great model for this task. The third key challenge is to post-process the model output and display the sunglasses. After we get the key points on the face, we want to render the sunglasses on the right place. And we find 3.js, which is an open source cross-browser library used to create and display animated 3D graphics in a web page through WebGL. It will be used to render the sunglasses onto user's face. And let's walk through the workflow diagram again. We take the video frame from web camera through TensorFlow.js data API and transform it into tensor that can be consumed by the model. We run face mesh model in the TensorFlow.js runtime to detect the facial key points, and then use the model output to put the sunglasses graphics on the right place. And finally, we use 3.js to render the sunglasses in the browser. And now let's start coding it. In the HTML file, we started by loading the TensorFlow.js library and the face mesh model from our hosted scripts. And next, we add a video element to hold the web camera as input, and another container to hold the rendered output. And here's how we will use the model. First, we load the model weights asynchronously, and then use the TensorFlow.js data API to get image frames from web camera, and then use the model to do an inference. The inference output is a JSON object containing the facial key points in 3D coordinates. And here we prepare the sunglasses image to be rendered in live web camera video. To display with 3.js, we need to have a scene containing the sunglasses image, a camera containing the video, and a WebGL renderer so that we can render the scene within the camera and display it. And finally, we create a loop through a request animation frame, and in each loop, we get an image from the camera, predict facial key points in the frame, and render the sunglasses onto the video. And let's see how the app finally looks like. Okay, so let me first add the face mesh render result. I'll just refresh the page and reload the model. And it takes several seconds to load the model. And okay, so you can see it shows the detected key points on my face and also the sunglasses. Okay, and this demo is built with a pre-trained model we provide. And we also support using pre-trained Python models in JavaScript. We provide a command line tool to bring TensorFlow saved model, TF hub model, and Keras model into JavaScript. It supports more than 200 ops, and also it supports both TensorFlow 1.x and 2.0. To use the Python model, first use the command line conversion tool we provide to convert the model into JavaScript-friendly format. And then the converted model can be loaded through TensorFlow.js API in JavaScript applications. And then finally, you can use the model in the same way as the model we provide. And what about other problems that there is no model available? We provide a Layers API, which is a Keras-compatible API for building models, and the lower-level op-driven call API if you need fine control of model architecture or execution. And let's see how to build and train a model from scratch with TensorFlow.js. First step is to import the model. And if you are working in Node.js, you can also use the tfjs-node library, which executes the TensorFlow operations using native compiled C++ code. And if you are on a system that supports CUDA, you can also import tfjs-node-gpu library to get GPU acceleration when doing training or inference. And this is what creating a convolutional model for an image classification task looks like. As you can see, it is very similar to Keras code in Python. We started by initiating a sequential model where the outputs of one layer are the inputs out to the next layer. And then adding a 2D convolutional layer and a max pooling operation with configurations. And then finish the model definition by adding a flatten operation and dense layer with the number of output classes. And once the model is defined, we compile the model and get it ready for training. Here we select a loss function and an optimizer for the training process. And model.fit is the function that drives the training loop. It is an async function, so we want to wait for the result. Once the model is done training, we can save the model. Here we save it to the browser local storage. We also support saving to a number of different destinations, such as local file system or remote URL. And finally, we can use model.predict to get a result from the trained model. And next, I want to show you the tech stack and upcoming features in TensorFlow.js. We provide 3 layers of APIs. The top layer is the pre-trained models ready to use out of the box. In the middle, we provide layers API to easily build and train model. And in the lower layer, we provide an op-driven call API, so users can do fine control of model architecture or for linear algebra calculation. On client side, including on browser and on mobile platforms running hybrid JavaScript applications, our library is using WebGL for acceleration. It detects the WebGL version and automatically uses it. And on server side in Node.js, we use TensorFlow CPU and GPU-C library under the hood. Soon, we will release support for headless GL backend as well, which will provide GPU acceleration without dependency on CUDA. And this is the core architecture of TensorFlow.js. We have multiple acceleration options for machine learning operations faster on both client and server side. You can bring Python Keras model and load it with layers API, or use TensorFlow saved model and execute it with core API. And this is the performance benchmark on client side. On laptop and iPhone, the mobile net inference time you can see is comparable to TensorFlow Lite. And we are working hard to improve the performance on Android. On server side in Node.js, which is using the TensorFlow C library, you can see the mobile net inference time is also comparable to TensorFlow Python. We just had an alpha release for React Native support. You can use TensorFlow.js directly inside the React Native app with WebGL acceleration and load models in the same way as browser. And this is a React Native demo app performing style transfer on an image. First, it's taking an image of the picture and then take the style image. And this is the final result. And we are very excited to announce that Google Cloud AutoML now supports TensorFlow.js. You can train customer models using AutoML Vision Edge for both image classification and object detection. All you need to do is to upload the images and labels in the AutoML page. And then AutoML takes care of creating the best model for your training data and provide evaluation details. You can also choose whether you want higher accuracy or fast prediction or best trade-off. And after training is done, you can export a TensorFlow.js compatible model and use it in your JavaScript application. No model building or training code is necessary, and you can get a model through clicking in the Google Cloud platform. And this is the sample code of using a model from Google Cloud AutoML. We provide APIs to load the AutoML model, and you can use it in the same way as all the other models in TensorFlow.js. As we mentioned in our keynotes, the beta users have already seen impressive performance improvements. And in the future, we will bring more pre-trained models based on real-world use case, such as auto-reply and conversation understanding. We are also bringing usability improvements for server-side inference. Soon, we will support native saved model execution without conversion. And we are developing new backends with Wasm and WebGPU to improve the performance in browser. And React Native will have a full release soon. And the TensorFlow.js community is building awesome and inspiring applications using machine learning in browser. We would like to highlight one such example from Mila. Mila researchers have built a radiology assistant tool to analyze chest rays and make disease predictions, all inside the browser app. To tell us more about this tool and how they use TensorFlow.js, I would like to invite Dr. Joseph Paul Cohen from Mila to come up on stage.
Thanks. Great. So, okay. If we take a look at the traditional diagnostic pipeline, there's a certain area where physicians are already using web-based tools to make and help them make diagnostic decisions about a patient's future. For kidney donor risk or cardiovascular risk, these are already online as early as 2006. So with advances in deep learning, making diagnostic predictions from chest x-rays using deep learning, the next step is to also put that online in a way that's usable by these doctors. You can imagine such use cases for this in emergency rooms where humans are time limited, so we want to have them make less mistakes, right? Especially if they're focusing on something and they don't focus on something else that may be important but not their immediate concern. You can also have rural hospitals, right, all over the world that can access things through the web, right? Maybe there's no radiologist nearby to help them make that decision, right? Maybe the country doesn't even have remote resources to aid in them making that decision. So using these tools could be the closest opportunity that physician has for a second opinion before they make a decision on the course of treatment. We can also imagine non-experts being able to triage cases for a physician to see, right? So things like pneumonia or pneumothorax are things that should immediately be brought to the attention of a physician. And maybe there's 200 cases to get through in the morning, and 6 of them have really life-threatening results that they should be able to see in those. So they should be looked at first, right? So we can aid in this, as well as identifying rare diseases. This is something we're still working on, but this is a kind of a nice direction that this tool could do. Good go. Great. All right. So Jan LeCun said this project was nice, so I include a quote here. Okay, so there's a few reasons why we need to kind of put a chest X-ray tool in a browser. Okay, so we could ship a desktop application. That would take money. We don't have any money. We're a university. Well, we don't have any money for this. So we need to be able to do this in a way that it's free, right? And we also can't pay for the computation of processing all these X-rays, right? So if we made some free web-based tool, we couldn't have a serving server that actually does the processing in a sustainable way forever that's not reliant on donations. So in this way, we just want to offload the cost to the user's device. And to have them install software themselves from GitHub is probably not something a physician is going to do. So instead, we can deliver all the code in a web browser, right? So there's absolutely no setup, right? It can run on any device that has a web browser. Essentially, definitely anything Chrome runs on, also works in Firefox and Safari. But we're able to deliver this in a very elegant way, right? Without any setup. And there's some other issues that are interesting to talk about in this case where we also have to give away this tool for free, because when we start charging money, we go into this regulatory space, right? Which is kind of the reason we do this project in the first place, that physicians and radiologists are scared of these tools because companies say, oh, they work really well. AI is like really able to read these tools, when the performance is not 100%, right? And we should be really honest as researchers talking to physicians to make sure they really know the extent of the power of these tools, right? So they can really see how this can impact them, right? So to kind of bridge the gap and make sure people aren't afraid of these tools. So getting these things in front of these radiologists so they can just play with them is a challenge, and there's a lot of stuff in the way. So the best way is just give them a URL they can go to. Nothing stands in the way. There's no IT department, there's no red tape at their hospital, there's no money that needs to be paid to make this thing happen. So it really enables that use case, and there's really no other way to do it unless you got the doctor to sit down in your lab and show them on your computer, right? So it's a really game changer. So we can compute DenseNet in a browser in about 1 second once it's loaded. We also need to do auto-distribution detection. So it's an interesting challenge for the kind of expectation matching of the physician or the radiologist and a tool. So we don't want to process images of cats or regular bones. We want to make sure that only correct x-rays go through, so we maintain a certain level of accuracy. We do this with an autoencoder. Autoencoders are great, which we also run in the browser. We also need to compute gradients. So why do we have to do this? We want to show a saliency map. And to do that, we need to compute the gradients of the image pixels to the output, right? We could ship 2 models. That would be like the simplest kind of code way, right? We ship one that predicts the actual pathology and another one that just computes the gradients for the input image. But that's a lot of work, and it's kind of annoying. So what we can do instead is just perform autodiff in the browser to make the new graph, which computes the gradients, right? Which is kind of magical. And then we compute on that graph and we get the gradients. We also do that with TensorFlow.js. So okay, thank you.
Thank you, Joseph. And another example I want to show you is developed by the community is the cognitive open tech group at IBM, who gave a talk on this yesterday, is developing a parasite detection web app, which runs an image classification model in the browser, so it is easy to deploy and run offline in the field. And also the library was launched last year, and in this March, we released version 1.0. We have seen huge adoption by the community with impressive downloads and usage numbers. And there are a lot of developers who are building add-on libraries and extensions on top of TensorFlow.js. And these are extending TensorFlow.js in a very useful way. And we have a variety of resources to help you get started. A couple I want to highlight is a book called Deep Learning with JavaScript, which is written by our colleague in TensorFlow team. It provides a variety of machine learning examples written with TensorFlow.js. And there are some courses available online. We have an official website hosting the guides, demos, tutorials, and our API documentations. The website also lists all the pre-trained models we provide. Our code is totally open source, and you can find them in our GitHub repo. And if you have any questions or idea, you can email us at tensorflowjs@google.com or join our Google group tfjs@tensorflow.org. And you can also try our demo and meet our team in the demo booth. Thank you.
Hi, and welcome to the TensorFlow YouTube channel. On this channel, we'll have a lineup of great shows for you, including Coding TensorFlow, where we explore what it is to write TensorFlow code together. TensorFlow Lite is TensorFlow's lightweight solution for mobile and embedded devices. Here's a sample piece of code, TensorFlow Meets, where you are the star, and we get to meet with you to talk and to learn and to share about all of the great things that you're doing with TensorFlow.
Just learning the basic mechanics and concepts, but seeing how it actually applies to their field.
I like this combination a lot.
There's also Ask TensorFlow, where we answer your questions marked on social media with the Ask TensorFlow hashtag.
What is the difference between TensorFlow Mobile and TensorFlow Lite?
One's mobile, the other's light.
That's right.
We'll also have lots of great content from events like the TensorFlow Developer Summit and special guests from other parts of Google and beyond. So hit that subscribe button now, and we'll see you there. Hi, and welcome to the TensorFlow YouTube channel. On this channel, we'll have a lineup of great shows for you, including Coding TensorFlow, where we explore what it is to write TensorFlow code together. TensorFlow Lite is TensorFlow's lightweight solution for mobile and embedded devices. Here's a sample piece of code, TensorFlow Meets, where you are the star, and we get to meet with you to talk and to learn and to share about all of the great things that you're doing with TensorFlow.
Just learning the basic mechanics and concepts, but seeing how it actually applies to their field.
I like this combination a lot.
There's also Ask TensorFlow, where we answer your questions marked on social media with the Ask TensorFlow hashtag.
What is the difference between TensorFlow Mobile and TensorFlow Lite?
One's mobile, the other's light.
That's right.
We'll also have lots of great content from events like the TensorFlow Developer Summit and special guests from other parts of Google and beyond. So hit that subscribe button now, and we'll see you there.
Consultare documenti storici, soprattutto documenti medievali, richiede sempre molto tempo, molta pazienza. In Archivio Vaticano abbiamo 85 km lineari di documenti, più o meno la lunghezza del Canale di Panama. Le scritture scritte nel Medioevo sono diverse da quelle che noi conosciamo. Se qualcuno mi chiedesse un giorno di trascrivere e tradurre tutti i documenti dell'Archivio Vaticano, sicuramente gli direi che è un matto.
Looking at this book, page by page, and trying to decipher, read and transcribe whatever is there takes an enormous amount of time. You would require an army of paleographers.
What I'm excited the most about machine learning is that it enabled us to solve problems that up to 10-15 years ago we thought unsolvable.
In Codice Razzi è nato da quest'idea di costruire un software per poter interpretare, per poter leggere quello che è scritto dentro i manoscritti. Quando abbiamo iniziato ad approcciare il problema ci siamo resi conto che una soluzione basata su reti neurali fosse assolutamente necessaria. La scelta su TensorFlow è stata abbastanza naturale.
Before using any kind of machine learning model, we needed to collect data first. You have thousands of images of dogs and cats in the internet, but there is very little images of ancient manuscripts. We built our own custom web application for crowdsourcing, and we involved high school students to collect the data. I didn't know much about machine learning in general, but I found it very easy to create a TensorFlow environment. When we were trying to figure out which model worked best for us, Keras was the best solution. The production model runs on TensorFlow layers and estimator interface. We experimented with binary classification with fully connected networks, and finally we moved to convolutional neural network and multi-class classification.
In poco tempo siamo riusciti a sviluppare e a testare le prime soluzioni.
When it comes to recognizing single characters, we can get 95% average accuracy.
Poter accedere a uno strumento informatico abbrevia notevolmente. Sciogliere certe abbreviazioni, comprendere un testo in quella scrittura così criptica è un qualcosa di eccezionale.
This will have an enormous impact. In a short period of time, we will have a massive quantity of historical information available.
I just think solving problems is fun. It's a game against myself and how good I can do.
Lo studio della storia è importantissimo per comprendere il nostro presente e per avere anche una prospettiva per il futuro.
Hello, my name is Alejandra.
And I'm Erickson.
And we're using machine learning to find potholes on the streets of Los Angeles.
LA has over 7,400 miles of roads and freeways.
That's a lot of roads and a lot of potholes to fix.
Right now, construction workers have to manually inspect roads for dangerous potholes and cracks, or rely on people calling in tips, which takes a lot of time.
While studying at LMU, we started to see if we could figure out a faster way to identify potholes throughout the city.
First, we needed data. So we rigged a camera to a car and we drove around to capture footage of different roads and freeways.
Then, we used TensorFlow, Google's open source machine learning tool, to develop a model that could quickly identify potholes, road cracks, and other weird stuff with a high rate of accuracy. Which means workers can spend less time finding potholes and more time fixing them.
You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's, and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code, predict the y when x equals 10? You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you.
हमारा खेत था तो जाते थे दोस्तों के साथ खेलते थे और वहाँ पे सारा मजा आता था फिर नदी आ गई तो काट लिया
घाघरा नदी सारे काट लिया गांव को कोई सूचना मिलती ही नहीं है अगर कोई सूचना मिलती तो हम लोग को मदद मिलते कोई मदद नहीं है हमारे लोगों को
Aid agencies are struggling to get help to millions of people affected by devastating floods across South Asia. It's thought to be the worst monsoon.
Thousands of troops have already been pressed into action.
It was extremely frightening because we had no warning.
One of the most important variables during a crisis is reliable information. There's so much work that's already been done by governments, by the UN and NGOs, and we're trying to learn from that work, build on that, and assist them with their goals. In India, where we're running our first pilot program, the government has thousands of people who are measuring the water level in rivers across India with what is effectively very long measuring sticks, which are called stream gauges, every hour, which allows them to know whether the river will overflow and flood, but it doesn't yet allow them to understand exactly what areas are going to be affected, what neighborhoods, or even what villages.
Any station calling? Any station?
चेतावनी में तहसील से साहब मिलती है अधिकारी जो हमारे होते हैं कर्मचारी वो हमें सभी सतर्क कर देते हैं कि बाढ़ आने वाली आप लोग ऊंचे आ जाइए नहीं नुकसान सब उससे पहले पता चल जाएगा
The response time is most crucial thing. Reducing the response time always plays very important and vital role in the whole disaster management framework. advancement in technology would help us better in spreading this message faster.
Flood forecasting was a very exploratory project. The big technical question was, can we have enough information to try to do forecasting that would be accurate enough to make a difference? Starting with the basic needs for getting information about what's going on, where is it happening, what should I be doing?
To be able to provide a forecast in real time, we rely on the government we're working with. We complement their effort by adding accurate modeling to that process. We start by collecting thousands of satellite images to build a digital model of the terrain. Based on these maps, we generate hundreds of thousands of simulations of how the river could possibly behave. We receive the measurements from the government and cross those measurements with our simulations. We can then send those forecasts to individuals using search, maps, and Android notifications. This is an example of an alert that we can produce. This alert is for Patna. This alert has over 90% accuracy. The lead time is incredibly important, even more than the specifics.
Any information we can give, they will use.
You want to show them the alert? Talking to people who directly experience severe floods and understanding what they really need is incredibly important for us to know how we can really help.
This is an opportunity to collaborate in a global scale. We are in very exciting time to use technology to try to make a difference.
I can't imagine a greater privilege than to do what we love and do it in a way that could actually help people directly in a very profound way.
Our hope for the future is to give people a few more days of warning before a flood occurs, and to use AI to scale this and provide these forecasts anywhere in the world, wherever people need them.
Extreme weather is changing. There's more extreme rainfall, heavy flooding, forest fires. There isn't really a signature done. Being able to predict these extreme events more accurately is kind of the big challenge that we're facing right now. There's 100 terabytes of climate data every day from satellites, from observations, from models. So climate data is a big data problem. We need things that are fast, that can sift through all of that data rapidly and accurately. And deep learning is almost perfectly poised for problems in climate science.
A lot of NERSC users are using TensorFlow. It's one of the more popular frameworks. We use TensorFlow to iterate quickly over different models, different layer parameters. For this particular climate project, to create the deep learning model, we started from segmentation models which have proven to be successful, for example, our satellite imagery segmentation tasks. And then we used TensorFlow to enhance the models until we found like a set of models which perform well enough for this specific task. But for the volume of the data, complexity of the data, the network required 14 teraflops. So if you want to do this on your workstation, it would take like months to train.
To really tackle these problems requires the largest computational resources that are available on the planet. So systems like the Summit supercomputer. It's 2 tennis courts in total size. I mean, this thing is state-of-the-art. It's 1,000,000 times faster than your common laptop. 3.3 exaflops. Just imagine what you do at your workstation, but now imagine having 27,000 times that power. We can do that now.
We were surprised how good it actually scales. 1,000 nodes, and 2,000 nodes, 5,000 nodes.
This was the first time anybody's ever run an AI application at this scale. Instead of having the climate scientists figure out how to write high-tune code, they could express things in a very natural way in Python in TensorFlow and get all the high-performance code that most HPC people are used to within TensorFlow.
We're now entering the space where AI can actually contribute to the predictions of these extreme weather events.
When you combine traditional HPC with AI, you can tackle things we never thought that we could tackle. Fusion reactor research, understanding diseases like Alzheimer's, cancer, right? That's incredible.
We've shown that with a high productivity framework such as TensorFlow, you can get to massive scale and you can get awesome performance and accomplish your goals.
Genetics, neuroscience, cosmology, high energy physics. That's immensely exciting for me.
the very last session. It's my great pleasure to introduce today Sujith and Dachen, who will be speaking to you about neural structured learning in TensorFlow. Thank you.
Hi everyone, I'm Sujith. I lead a few machine learning teams in Google AI. We work a lot on how do you do deep networks and build machine learning systems at scale on the cloud with minimal supervision. We work in language understanding, computer vision, multimodal applications, but also we do things on the edge. That means how do you take all these algorithms and fit it to compute and memory constrained devices on the edge. And I'm here today with my colleague.
Hi, I'm Dachen, and I'm working with Sujith on neurostructural learning and all the related topics.
So let's get started. You guys have the honor of being here for the last session of the last day. So kudos and bravo. I mean, you are really dedicated. So let us begin. So we are very excited to talk to you about neural structured learning, which is a new framework in TensorFlow that allows you to train neural networks with structured signals. But first, let's go over some basics. If you're in this room and you know about deep learning and you care deeply about deep learning, you know how typical neural networks work. So if you want to take, for example, a neural network and train it to recognize images and distinguish between concepts like cats and dogs, what would you do? You feed images like this on the left side, which looks like a dog, and give the label dog and feed it to the network. And the process by which it works is you adjust weights in the network such that the network learns to distinguish and discriminate between different concepts and correctly tag the image and convert the pixels to a category. This is all great. All of you in this room probably have built some network. How many of you have actually built a neural network? Great, and this is the last session, last day, but still, very happy that you're all with me here. So what is the one thing? I mean, it's all great. We have like a lot of fancy algorithms, very fancy networks. What is the one core ingredient that we need when we build a network? So almost majority of the applications that you work on, we require label data, annotated data. So it's not one image that you're feeding to this network. You're actually taking a bunch of images paired with their labels, cats and dogs in this case, but of course it could be whatever, like depending on your application. But we feed it like thousands or hundreds of thousands or even millions of examples into the network to train a good classifier, right? Today, we're going to introduce neural structured learning, which is a framework. We're happy to say it's supported in TensorFlow 2.0 and Keras, and it allows you to train better and more robust neural networks by leveraging structure in the data. So the core idea behind this framework is that we're going to take neural networks and feed it, in addition to feature inputs, structured signals. So think of the abstract image that I showed you earlier. Now, in addition to these images paired with labels, you're going to feed it connections or relationships between the samples themselves. I will get to it, what these relationships might mean. But so you have these structured signals and the labels, and you feed both into the network. You might ask, like, what do you mean by structure, right? Structure is everywhere. In the example that I showed you earlier, if you look at images, just take a look at this graph here. The images that are connected via edges in this picture here basically represent that there's some visual similarity between these. So it is actually pretty easy to construct structured signals from day-to-day sources of data. So in the case of images here, it's visual similarity. But you could think of what if you tag your images and created albums. That represents some specific concept. So everything within an album or a photo album has some sort of a connection or interaction or relationship between them. So that represents another type of structure. It's not just for images. We can go to like more advanced or like completely different applications. Like if you want to take like publications, scientific publications, or news articles, and you want to tag them with their topic. One simple thing, take biomedical literature. All the papers that are published, whether it's Nature or any other conferences, they have references and citations to other papers. That represents another type of structure or link. So these are the kind of structures that we're talking about here. Relationships that are exhibited or like modeled between different types of objects. In the natural language space, This occurs everywhere. If you're talking about doing search, everybody has heard of knowledge graph, which is a rich source of information which captures relationships between entities. So if I talk about the concept Paris and France, the relationship is one is a capital of the other, right? So these sort of relationships, it's not typical to capture and like feed them into a neural network, but these are the kind of relationships which are already existing in day-to-day data sources. So why not leverage them? So that is what we try to do with the neural structured learning. And the key advantages, I mean, before we talk about what it does and how we do it, why do you even want to care about it, right? I mean, like, what is the benefit? So one of them is, as I mentioned earlier, it allows you to take this structure and use it to train neural networks with less label data. And that's the costly process, right? So for every application that you want to train, if you had to collect a lot of rich annotated data at scale for millions of examples, it's going to be a tedious task. Instead, if you're able to use like a framework like neural structured learning that automatically captures the data structure and relationship, and with minimal supervision, you're able to train classifiers or prediction systems with the same accuracy, that would be a huge boon. Like, who wouldn't want that, right? That's one type of benefit. Another one is that typically when you deploy these systems in practice, in real-world applications, you want the systems or networks to be robust. That means you train them once. You don't want, if the input distribution changes or data suddenly changes or somebody corrupts the images with adversarial attacks, suddenly the network to flip the predictions and go bonkers, right? So this is another benefit where if you use neural structured learning, you can actually improve the quality of your network and also the robustness of the network. So let me dive a little deeper and give you a little more insight into the first scenario, right? Take document classification as an example. So I'll give you like probably some example that you probably have at your home, right? Imagine you have a catalog of or a library of books in your home, and these are digitized content. And you want to categorize them and neatly arrange them into like specific topics or categories. Now, one person might want to categorize them based on the genre. A different person might say, oh, I want like it to belong to the same period. A third person might say, oh, I want to capture different books that have the same kind of content or phrases or words that appear in the same by the same author or by like based on some certain aspect, like there's a like a particular plot twist that you have that is captured in different books, and I want to arrange them based on that. So you can think of not everybody's needs are the same. So are you going to collect and annotate enough label data for each of those tasks, to create a network that can, with very high accuracy, distinguish and classify them into these genres? Probably not. So on the one hand, you have plenty of data. The raw book content is available to you, or raw news articles are available to you. There's plenty of raw text available to you. But it's hard to construct this labeled annotated data, right? So this is where neural structured learning, or NSL, going back to the previous example, we can model the relationships between these different inputs or samples using structure. Again, I will tell you what the structure means, but pair with a few labeled examples and then train a network that is almost as good as the network that is trained on like millions of examples. So imagine you could, for your application, only use 5% or 10% of the labeled data and train as good a classifier or like a prediction system. So that's what we're trying to do and help you do with neural structured learning. And I said structure. How do you come up with this structure, or how do you do this for document classification? I'm going to give you a forward reference here. Dacheng is going to talk a little bit more about that as well. So there is a hands-on tutorial for the exact example that I told you, document classification with a graph, and you can go to the Neural Structured Learning TensorFlow website and try this out for yourself, all within just a few lines of code. All you need to do is construct the data in the right format, and with a few lines of code, you should be able to run the system end-to-end. Switching to the second scenario, it's great to have high-quality models. We have seen that neural networks have the capacity to train really, really good quality models, especially as you increase the number of parameters. But Robustness is an important concept and actually an important criteria when we deploy this to real-world scenarios. For example, if you have an image recognition system and suddenly the network flips its prediction because the images are corrupted, this is not a good thing. And this is not just for image classification. It could be for text or any kind of sensor data. Here's an example. Take the image on the left. What do you think it is? It's a panda. Take the image on the right. What do you think it is? Anyone who disagrees it's a panda? Basically, your neural network is saying that both of these images are pandas. But that's not what happens if you actually train a real neural network, like, for example, ResNet or whatever, the state-of-the-art network, and you try to apply it to the two images. The first one will be correctly recognized as a panda. The second one will be recognized by a completely different concept, in this case, a gibbon. And the reason it happens is if you zoom in really close, the second image is actually an adversarial example. It's actually created by adding some noise to the original image. But these are like so tiny, it's very imperceivable for the human eye. But the network, based on these changes in the pixels, flips its prediction completely. Imagine this happening, in a live system, right? So you don't want these things to happen. So you want the networks to be robust. So this is where NSL comes again. And again, we're going to use the same concept. Use the structure in the data to train more robust models. And here the structure is slightly different from the one that I mentioned earlier. Earlier, we were talking about explicit relationships or model as a graph. Here, we are going to construct that structure. So we take the original image, and we also generate a perturbed image or an adversarial example for that original image. Now, these two images are joined via a link. So there's a relationship between them. The difference is this is dynamically generated during the learning process, as opposed to the earlier case where somebody gives you a knowledge graph or these structured signals, or you construct them from some data source. And what we try to do here is, using the structure, we already know the label for the first image is a panda. We're trying to force the network to learn that the perturbed image also should be classified as a panda. So that's at a very high level how this works. Again, if you want to try this out for any of your network or in any application, you can go, there's a tutorial which allows you to do this, like use the API. So NSL enables both the neural graph type of learning and also the adversarial learning, and you can just go to the website and like run through the code example, all with just a few lines of code. You will see more details later in the talk. So this is at a high level how and why we would want a framework like NSL and the power of using it to enable more robust networks and also build networks with, that can be trained with minimal supervision. These are like very, very handy when you want to build like, applications on the fly and very, very custom applications that do not fit like the regular mold. Let us now dive a little deeper into how we do this, right? What the framework is doing. So in the first paradigm, as I said, structure is going to be used to model and as an input and network. So we call this paradigm neural graph learning. So the core idea is that in addition to these feature inputs that you're familiar with, like pixels for image classification, or let's word features or phrase features or sentence features for document classification, in addition to those feature inputs, you're going to pass in structured signals modeled as a graph. So you might ask, by the way, at this point, like, where is the graph coming from in these settings, right? In some cases, it might be given to you, as I said, like the citation graph, knowledge graph. In other cases, you can actually construct a graph. We're very happy to say that we provide tools, again, you will hear more about this, that allow you to construct these graphs from sources of data like word embeddings or image embeddings. So now the goal here in neural graph learning is the network is going to be forced to jointly optimize both the feature input and the structured signal simultaneously. Let's see how that happens, like diving in deeper. If you're trying to look at what exactly the network is learning, every network is trying to optimize some loss. So in image classification, what is the loss when you take the pixels, pass through the network, get some prediction? What is the error incurred between the predictions and the true label? So in NSL, the neural graph learning setting, we call these networks trained in this mode neural graph machines. What we're trying to optimize is two components. One is the standard loss, which is in image classification, is the loss incurred when you pass the pixels through the network, get the predictions, and measure the error with the true labels. The other component is going to be based on the structured signal or the graph that you provided. And where that comes in is if I have an image like that looked like the pit bull dog, that's labeled as a pit bull. If I have a different image which through my structured signal is like sort of has an edge with the original image, then the network is forced to learn that the source image and its neighbor in the graph should learn similar representations. That means you're trying to say that respect the structure that you provide as input and also try to optimize the supervised loss. Now, this is very flexible, as you can imagine. You can use the API to change the formulations. That means instead of a supervised loss, if you want to do unsupervised learning or a very different kind of loss, you can actually change the first component very easily. And just another quick note, like we don't have time for that, but like we're happy to answer more questions at the end. The losses themselves, the type of losses are also customizable. You can use L2 loss, cross entropy, depending on the kind of applications. You can even use ranking losses, if you will. So this now makes it very, very easy for you to train a wide range of applications in a different learning setting, like whether it's unsupervised, supervised, or ranking, or like classification. But at the same time, you'll be able to pass in some structure in a seamless manner. Here's an example. So the NSL, neural graph learning, take image classification. You start with some samples, as I said, the pixels, and you also have a structure. In this case, the images are connected in the graph based on some user interaction signal, or basically, for example, as I showed you, like they belong to the same album, or there's some sort of structure tying them together. Assuming this is given to you, we pass this through the network. Both the sample and its neighbors are passed simultaneously through the same network, and the network is learning to optimize within each layer, and this is also configurable, by the way, to push the embeddings for neighbors closer to each other. That means two images that are connected in the graph should learn similar embeddings when passed through the network. Simultaneously, you should also optimize that they should learn the correct predictions. So if one of them was labeled as a panda, then you also want the prediction error to be minimal. So both of these parts are being optimized jointly. Okay, so hopefully this gives you an idea of how we use graph learning or neural graph learning and enable this via the neural structured learning framework. As I mentioned, structure can come in different forms. That was an explicit structure we provided as a graph input, but we can also do implicit structures, and this is where the adversarial learning type of paradigms are enabled using the NSL framework. And here, again, we're going to jointly optimize features and structure, except the difference is the structure is now induced during the learning process by constructing adversarial examples to the original input. So if you have an xi as an input, you create an xi prime, which is an adversarial version of that, and these two are connected, and there is some sort of weight, based on the, this is configurable. And this structure is now passed through the network, and the network is forced to optimize both of them to the same embeddings or representations inside. These are all great. So we, as I mentioned, this sort of opens up a host of new kind of application or like training scenarios. The best part about this is if you're thinking, oh, now how does this work with transformers or ResNets or different kinds of network structure doesn't matter here. You can use this with any type of network structure. That's the best part. RNNs, transformers, like resonance convolutions, like you have combination of CNNs, LSTMs, doesn't matter. These are sort of learning strategies, right? You can actually build a network, but enable NSL both in the adversarial and in the neural graph setting very easily with very few lines of code in TF 2.0. And to tell you more about that, I'm handing it over to Jiacheng.
All right. Thank you, Sujit. Next, we are going to introduce the libraries, tools, and trainers provided by the Neural Structured Learning Framework. Everything here is compatible with TensorFlow 2.0, so you could train the neural nets with structured signals while enjoying all the great features from TensorFlow 2.0. This is the training workflow we just mentioned previously. Every segment in red here is a new step introduced to the workflow to train with structured signals. And neurostructural learning provide libraries and tools for these steps. Let's first take a look at the left part of the workflow. The training samples and neighbors from the same neighborhood are packed to form the new batch. Notice that in the batch, each training sample is extended to include the neighborhood information. To achieve this, in the neurostructural learning framework, we provide standalone tools such as BuildGraph and PackNeighbors that a user could invoke directly. We also provide functions that users could integrate into their own custom pipeline. And you may notice BuildGraph and PackNeighbors here are listed both as binaries and functions. This is not a typo. This means they could be invoked both as a binary or as a function. Next, let's take a look at the right part of a figure. Again, we provide libraries for these new steps introduced to enable graph regularization. Both the training sample and its neighbor will be fed to the neural network. And onPackNeighbor features is for this purpose. The model in this illustration is convolutional neural net, but it can be any type of neural network, not just limited to the convolutional neural net. Then the difference between the sample and its neighbor embedding is calculated and added to the final loss as the regularization term. In addition, we also provide libraries to generate the adversarial neighbors as implicit structure signals for regularization. Finally, we also provide the Keras APIs for user to easily build Keras trainers with graph regularization or adversarial regularization. The Keras API from neurostructural learning support all three types of model building, either via sequential, via functional API, or via subclassing. This is just a subset of tools and libraries we provided in the neurostructural learning framework. Please visit our website to learn more about the tools and APIs in neurostructural learning. The first step, if you want to use neurostructural learning, is to do a pip install. Here, we provide a code example demonstrating the API from the neurostructural learning library. We first need to read the training data. Note that the data here are preprocessed by the tools or functions to incorporate the graphs into training samples. Next, the user could build custom models and treat it as the base model. The user could build this model, the base model, use any of their favorite Keras API, like we just mentioned, sequential, functional, or subclassing. After the base model is built, we use the API to wrap around the base model to enable the graph regularization. There are several hyperparameters we need to configure. For example, we need to specify the maximum number of neighbors considered during the regularization. Also, for each hyperparameter, we provide default values set to a certain number that we know empirically they work well. After we enable graph regularization in Keras model, the rest is just the standard Keras workflow: compile, fit, and then eval. That's it. Within 5 lines, we are able to enable graph regularization. And 5 lines actually include 1 line that's a common, not the actual logic implementation. Here, let us show some results of a model trained with structure signals. The task is to conduct the sentiment analysis on the IMDb movie reviews. We want to point out that this result is just from one of our internal experiments. Your actual mileage may vary from task to task, from data to data, or from model to model. The x-axis here represents the amount of supervision, which could be converted into the amount of label example. And y-axis here represents the model accuracy. The left figure shows the performance of a bidirectional RSTM, and the right figure shows the performance of a feed-forward neural net. As you can see, when we have lots of training examples, when the amount of supervision is high, there's actually not much performance difference. But as soon as the amount of supervision dropped to 5% or even 1%, training with structured signals lead to more accurate models. Usually the improvement is more than 10%. If you are interested in more results, please refer to our paper. So training with structured signals sounds really great, but sometimes we do not have a structure. We do not have a graph to begin with. So what should we do? Neural structure learning provides two methods. The first one is to construct the graph or construct the structure via data preprocessing. And the second one is to construct such structure via adversarial neighbors. Let's focus on the data preprocessing one first. Again, let's take document classification as an example. Given a sample document, how do we know if another document is similar enough to be the neighbor document? These documents will be projected to the embedding space. For example, we could use the pre-trained BERT embedding that's mentioned in the earlier TensorFlow talk, and to project all these documents into generated embedding. Documents that are closer in the embedding space are assumed to have similar semantics. Next, we examine the similarity between two embeddings. Cosine similarity or other metric could be used here. If the similarity is higher than a predefined threshold, we treat these two documents are similar enough, and therefore we add an edge between these two documents to make them neighbors. By repeating this process, we could construct a structure or construct a graph among all the data via the data preprocessing. After we have the graph, the rest of the training flow is exactly the same as we mentioned before, the one as if the graph is given. Let's again take a look at the actual code example. We first load the training data and test samples from the IMDb dataset. Next, we load the pre-trained embedding model from the TF Hub. The embedding model we use here is a swivel model, but feel free to replace it with your favorite pre-trained embedding model, such as BERT. Next, we project the text or the document of each review from IMDb to the embedding, so we could calculate a similarity between two reviews in the embedding space. Remember, when two reviews are closer in the embedding space, we assume they share similar semantics. After we project text to the embedding, we use build graph function provided by the neural structure learning to construct the graph. When invoking this function, we also need to provide a similarity threshold, which is point A in this case. After we have the graph, we call packNeighbor function to incorporate the neighbor samples into each training sample. Here, for each sample, 3 neighbors are considered. After we augment the training data with graph signals, everything is just like the first code example we show. Read data, build a base model via either sequential, functional API, or subclassing. Feels familiar? Then we use the neural structure learning API to wrap around the base model to enable the graph regularization. Again, the rest of the workflow is just the standard Keras flow: compile, fit, and eval. So we also provide the hands-on tutorial, step-by-step tutorial on our website. So feel free to visit the website and play it by yourself. The second method to construct a structure or construct a graph signal is to build a graph dynamically by adding adversarial neighbors. For each training sample, we find a malicious perturbation based on the reverse gradient direction. In other words, that perturbation is designed to confuse the model by most, which means to maximize the loss. Then, this malicious perturbation is added to the original training sample to create the adversarial neighbor. Again, the design of adversarial neighbor targets at confusing the model by most, which is to maximize the loss. Then we add an edge between this adversarial neighbor and the original training example. And therefore, we have constructed a graph or constructed a structure. This is the code example using adversarial Keras model from neurostructure learning. Again, feel familiar? In addition to these 3 lines, everything else followed the same workflow introduced before. Neurostructure learning has been widely used in many products and services in Google. For example, learning image semantic embedding. Here, we provide 6 examples, 2 for each semantic granularity to illustrate the difference from coarser to ultra-fine granularity. The object in the right is the Golden Gate Bridge. The Golden Gate Bridge is the steel red bridge. But not all the steel red bridge, such as the image in the middle, are the Golden Gate Bridge. Learning such embedding is a challenging task, partly due to the large variation seen among images that belong to the same class or to the same category. Learning image embedding to capture fine-grained semantics, however, is the core of many image-related applications, such as image search, either queried by traditional keywords or the example query image. This is the overall neural architecture used to learn the image embedding. And again, feel familiar? This is exactly the same workflow we introduce again and again in this talk. And since this talk focuses on neurostructure learning, we will not introduce in detail about other techniques, such as sample softmax, used to train a model. If you are interested, please refer to our paper. Let's zoom in into the structure part. The graph used here is a co-occurrence graph. Essentially, the co-occurrence graph is trying to answer the following question. Given one image is selected, what are other images that's sufficiently similar that will also be selected? Say the query is the white English bulldog. If 2 images are co-occur for many, many times, we add an edge between these 2 images, making them neighbors. So here are some experimental results. For each query image, we provide the top 3 nearest neighbor based on the image embedding learned. The image color by green are rated to be strongly similar with the query image by human raters, whereas the image color by red is not so similar. For example, in the left figure, when the image query is a white squirrel, other white squirrel can be correctly retrieved by using an embedding learned from the neurostructure learning framework. In other words, learning with structure is able to capture image semantics much closer to actual human perception. So, to recap, training with structure is very useful. Last label data are required to effectively train a model. Also, learning with structure signals lead to the more robust model. And neurostructure learning provide APIs, provide tools, and Keras model. And also, it works for all types of neural net, either feed-forward neural net, convolutional neural net, or recurrent neural net, or any custom neural net you designed. This is probably the most informative slide of this talk. You can learn tools, libraries, or hands-on tutorials in detail in our website. Also, please start our GitHub. We do take GitHub issues, and we would love to hear from you. We are looking forward to developing this framework with all of you to make this framework more comprehensive. We will be waiting for your pull request on GitHub. Thank you. Do we still have time for a question? Okay, so I think we still have some time for questions.
You may have to use the mic.
the build graph function that you mentioned, so does it do like pairwise comparison across all the all the items, or like
all the all the samples, not only training? Yeah.
I see. So for
both label and unlabeled samples.
I see. So for IMDb dataset, reviews dataset, how long did it take to build graph?
So it heavily depends on what machines you are using, right? So since IMDb review is a relatively small data set, so building graph will not take too long.
I see.
One addition to that, so it turns out you don't really have to do all pairs comparison. There are much faster techniques. So we stay tuned. I think we're in the process of releasing other tools which will make it much faster, even on single machines, right? Without having to do if you have million example, you don't need to do million cross million, right? Yeah.
Sure. So we actually tried to use that, and it took a lot of time. So instead of that, then we use phase.
Great. So you are probably going to be the first user for something that we're going to release soon then.
Yeah. Okay. Thank you.
Very nice. Just so that I think I understand what you're doing. It looks like you're taking images and then GAN-generated images from the generator, associating them, and thereby negating the ability of GANs to deceive a neural network. Is that correct?
It does not necessarily have to be the GAN structure. The idea is any network that you're trying to learn, we're using the gradients that are backpropped and reversing the gradients to construct a, sort of a noisy example, if you will. And the reason to do this is that, and then while doing the training, is that next time the network sees this noisy example, right, it will still learn to correctly identify it rather than, flipping the predictions. And so we're trying to make the intermediate layers and also the predictions robust. Yeah.
In that loss function, it looked like it had something from a discriminator plus a generator or something, that notation, or maybe it was just a coincidence.
Which equation?
That loss function that you had that you're trying to minimize?
Oh, so the loss function just has two components. The first one is the supervised loss, or whatever loss your application has. The second one is that we're factorizing the loss over neighbors, like source images and neighbors, right? And in the case of adversarial, that neighbor image is basically constructed, and the weight is basically whatever weight that you're assigning to the adversarial image. Yeah.
Very good, thank you.
Very neat idea, thanks. But I think in page 34, the graph looked a bit weird to me. Can you open the...
Page 34?
And when you compare it with the standard, this one. Yeah, this graph looked a bit strange to me. How many samples at each point you generated? What are the error bars in here?
So basically, this is the error bar is from the test data set. It's not from the training.
No, what I meant, how many trials?
Training trials.
Yeah, how many times you start from a different seed and train the networks and then get these results?
How many training trials? I do believe we have 5 trials.
So each point is 5 samples?
Yeah.
Okay, average of 5 samples, okay.
Yeah, so I mean, technically, as I said, that depends on the network that you're training. Typically, what you would expect is, even if the network is really powerful, the gap to increase. So there's some, in the 2% thing, you'll see there's a, the gap is lower than what the 5% is. But that's just based on this data set, right? So typically what you see is the gap increase as the supervision ratio goes lower.
Yeah, this is what I would expect. But if you look at it for 2% and then 0.5%, they're coinciding.
Yeah, so this is just one example. We would recommend that you try it on your own data set, right? And on one of the networks that you build.
Hi, how you doing? I was curious how you guys might apply this to, say, segmentation or to video classification.
I think there are a couple of different ways. In the video classification, you can look at videos that are sort of related, right? Similar, let's say from the same channel, for example, right? And you have similar kind of content, or the metadata kind of matches. You can actually now create these links between these different videos. And assuming that you have a way of processing through convolution networks all these frames into some representation, you're going to apply this regularization in the NSL framework to say that, hey, these related videos all should sort of be optimized to learn the same prediction. There are many other ways we can talk offline about that.
Okay, thank you.
If we're talking about
Sorry.
Last question.
Yeah,
maybe.
okay.
Last question.
Yeah, I have two actually. Sorry. So if we're talking about data augmentation, so from do you compare the classical principles like distortion, I don't know, blurring, stretching, and all this kind of stuff compared to the adversarial generated samples? Is there any benefit of using one versus another in this case? Like why adversarial generated samples versus, let's say, some classical principles?
Because the distortion and rotation are predefined, like transformation functions that we have, right? The adversarial, it depends on the data and the network, and you're using the gradients that are backpropped to like create like an equivalent example, the hard example, if you will. Like for transformations, everybody knows, hey, this is the rotation, you apply rotation or you're blurring, right? But what if like somebody attacks and says like, it's not a rotated image, right? But in fact, like I take like pixels here, pixels there, and I sort of transform them or blur them. That's a very different kind of transformation functions. So here you're trying to do this across the board using the learning process and the gradients that are being learned in, for the network at that layer. Does that make sense?
And the second question, when the network sees the feedback from the graph that actually adversarial neighbor gives you a completely low score on the example, but the network itself is pretty sure that the class is there. So how does it resolve on this level when you have a pretty convinced scenario versus adversarial neighbor?
I think the clarification may be referring to the given mentioned. So just to clarify, the adversarial example does not necessarily have that wrong label during the learning process. We're constructing it on the fly, and we're making the network force it to. We just tagged it as, hey, that is a given if you didn't apply the adversarial learning.
Yeah, but you have the feedback from the graph that says that the classification is wrong here, so you try to regularize it. And but by this moment, the network is already pretty much convinced that it's not a gibbon, for example. But the graph tells that it's still like the class is wrong. So how does this resolve?
So a quick add on this is actually in some experiments we apply the correct label to the adversarial example. In a previous slide, the adversarial example, we will have the panda as label instead of gibbon.
All right. Okay.
So you could think in this way. This sample is very confusing to the model, but we still supervise model to learn the correct label, and therefore later on the neural network will be more robust.
Okay, clear. Thank you very much.
Right. Thank you.
Thank you.